The universe didn't make our solar system safe. It made it a laboratory of horrors. And the most terrifying thing about it is this: we live here, right now, less than 2 billion miles from the chair you are sitting in. Winds are screaming across a frozen world at 1,200 miles per hour. That is faster than the speed of sound, faster than a bullet, faster than anything the atmosphere of Earth has ever produced. On another world, closer than that, a storm larger than our entire planet has been raging for 400 years without stopping. Its winds could peel the surface off a mountain, and it shows no sign of slowing down. Elsewhere, on a moon that looks almost Earth-like from orbit, rain falls through the sky and pools into lakes and rivers. Except the rain is not water, it is methane, and the temperature is 290 degrees below zero. These are not distant exoplanets orbiting alien stars in some unreachable corner of the galaxy. These are our neighbors, the worlds we share our solar system with. The planets and moons we have known about for centuries, photographed with our best telescopes and sent spacecraft to visit, and every single one of them would kill you in seconds. For decades, we have treated our solar system like a quiet suburban street, familiar, predictable, almost boring compared to the exotic chaos of distant star systems. But we have been looking at it wrong, because hidden in plain sight, in the planets we learned about in grade school, are some of the most extreme, most hostile, most physics-defying environments in the known universe. And the more we study them, the less we understand how they got that way. This is the story of the 8 most terrifying worlds in our solar system, and why they matter more than we ever realized. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. You look up at night and see a handful of dots, maybe 5 planets on a good evening if you know where to squint. Venus hanging bright near the horizon, Mars looking faintly rust-colored if the atmosphere cooperates. Jupiter, steady and bright, occasionally flanked by a moon or two if you've got binoculars. Saturn if you're patient. They look peaceful, distant, harmless, like Christmas lights someone hung too far away to bother you. That is a lie your eyes are telling you. Those dots are not peaceful, they are not harmless, and they are absolutely not distant in any sense that should make you comfortable. Our solar system, the one you live in right now, the one you've been riding through space your entire life at 500,000 miles per hour, is a haunted house. A collection of worlds so hostile, so alien, so fundamentally wrong for anything resembling life, that if you were dropped onto their surfaces without warning, most of them would kill you in under a minute. Some in seconds, a few, if you were unlucky, might take longer. This is not science fiction. This is the neighborhood. For most of human history, we did not know this. The planets were lights. They moved, which made them interesting, but they were untouchable, abstract. You could watch them drift across the sky and imagine whatever you wanted. Gods, omens, clockwork perfection, the universe as a neat diagram where everything had its place and its reason. Then we built telescopes. Then we built rockets. Then we sent machines to go look, and the machines sent back pictures, and the pictures told a very different story. Venus is not the goddess of love. It is a furnace wrapped in acid clouds, spinning backward under a sky that crushes steel. Mars is not the god of war. It is a frozen desert where the air is too thin to breathe, and the dust will poison you slowly if the cold does not kill you first. Jupiter is not a benevolent king. It is a hurricane the size of 3 Earths that has been raging for centuries, wrapped around a planet so violent that its radiation belts would fry every circuit in your body before you got close enough to see the storms properly. We named these places after myths. We should have named them after warnings. The scale alone should bother you. Our solar system is not small. If you could somehow freeze it in place and drive a car at highway speed from the Sun to Neptune, the trip would take you about 6,000 years. You would pass Earth in just under 200 years, Mars a few hundred more after that. Then you would spend the next 5,000 years driving through nothing, just empty black, occasionally passing a gas giant so large that Earth would vanish into one of its storms like a marble dropped into a swimming pool. The Oort cloud, the shell of icy debris at the solar system's edge, extends so far out that light from the Sun takes over a year to reach it. A year, at the speed of light. That is the radius of the neighborhood you are standing in. And inside that radius, there are 8 major planets, 5 recognized dwarf planets, over 200 moons, millions of asteroids, billions of comets, and not one of them, not a single one aside from the rock you are currently standing on, would let you survive on its surface for more than a few minutes without technology specifically designed to keep you alive. Even the moon, our moon, the one you can see from your bedroom window, sits in a vacuum at temperatures that swing from 250 degrees Fahrenheit in the sunlight to 250 below in the shade. The dust is sharp enough to cut through fabric. There is no air. There is no water. There is no sound. You would boil and freeze at the same time. That is the closest planetary body to Earth. It is 250,000 miles away, and it is already trying to kill you. Now go farther. The paradox is that these places look so familiar from a distance. You see pictures of Mars, and it looks like Arizona. Rocks, sand, a distant horizon. You could almost imagine putting on a jacket and going for a walk. Then you read the specs. The average temperature is -80 degrees Fahrenheit. The atmospheric pressure is less than 1% of Earth's. It is not enough to keep liquid water stable on the surface. If you stood on Mars without a suit, the lack of pressure would cause the moisture in your lungs and eyes to start boiling. Not because it is hot, because pressure is what keeps water liquid at body temperature, and Mars does not have that pressure. You would not explode the way movies like to show, but you would swell. Your blood would not boil, not exactly, but the dissolved gases in your bloodstream would come out of solution. You would lose consciousness in about 15 seconds from lack of oxygen. You would be dead in 2 minutes. And the entire time you would be freezing. That is Mars, the planet we talk about colonizing. The one we send rovers to with names like Curiosity and Perseverance. It is the 4th rock from the Sun, and it is a death trap. Venus is worse. Venus is so much worse that it barely makes sense. It is the 2nd planet from the Sun, closer to Earth than Mars is, and it is the single most hostile major body in the inner solar system. The surface temperature averages 480 degrees Celsius. That is 900 Fahrenheit, hot enough to melt lead, hot enough to make your bones glow. The atmospheric pressure at the surface is 92 times what we experience on Earth, 92 times. If you stood on Venus, the air would crush you with the same force you would feel if you were swimming 900 meters below the surface of Earth's oceans. Except instead of water, you are being crushed by an atmosphere made mostly of carbon dioxide, wrapped in clouds of sulfuric acid, blowing past you at 230 miles per hour. Venus is the planet we named after beauty. It is the evening star. It is the brightest object in the night sky after the moon. And it would kill you so fast that we have never managed to land a probe there that survived more than a couple of hours. The Soviet Venera landers, the toughest machines we have ever dropped onto another planet, lasted 127 minutes at most before the heat and pressure cooked their electronics. One of them sent back a single photograph of the surface before it died. Flat rocks under a dim orange sky. It looked almost peaceful. Then the camera stopped working. You start to notice a pattern. The planets that look calm are not. The planets that look empty are not. And the planets that look like they might, in some distant, theoretical way, be explored by human beings one day, are lying. They are all lying. The solar system is not a collection of destinations. It is a gauntlet. Now go farther out, past Mars, past the asteroid belt, where millions of rocks tumble in the space between the inner planets and the giants. Enter the realm of Jupiter. Jupiter does not have a surface, not in any way you would recognize. It is a ball of gas wrapped around a core of liquid metallic hydrogen under pressures that do not exist anywhere on Earth. The outer layers are mostly hydrogen and helium, the same stuff the Sun is made of, whipped into bands of color by winds that blow at 350 miles per hour. The Great Red Spot, the most famous storm in the solar system, is a hurricane larger than Earth. It has been raging for at least 350 years, possibly longer. We do not know when it started. We only know it has not stopped. The radiation around Jupiter is so intense that it would kill you in minutes. The magnetic field is 20,000 times stronger than Earth's, trapping charged particles in belts that stretch for millions of miles. If you flew a spacecraft through those belts without shielding, the radiation would destroy its electronics. If you flew through them in person, it would destroy you. Not over weeks or months, the way radiation poisoning works on Earth. Fast. The kind of exposure that cooks tissue. And Jupiter is not even the worst of the gas giants. It is just the closest, the biggest, the one we know best because we have sent the most probes there. But its siblings are stranger. Saturn, with its rings, looks elegant in photos, delicate. The rings are made of ice and rock, some chunks the size of houses, all of them moving at thousands of miles per hour in a flat disk so thin that if you scaled Saturn down to the size of a piece of paper, the rings would be thinner than a human hair. The planet itself is less dense than water. If you could find a bathtub large enough, Saturn would float. That sounds harmless until you remember that it is still a gas giant with winds clocked at 1,100 miles per hour and a hexagonal storm at its north pole that is wider than Earth. Then come the ice giants, Uranus and Neptune, the two planets at the edge of the classical solar system, so far from the Sun that their atmospheres are made of methane and ammonia mixed with hydrogen and helium. Uranus spins on its side, tilted at an angle of 97.9 degrees. Something hit it early in its history, knocked it over, and it has been rolling through space like a barrel ever since. Neptune, even farther out, holds the record for the fastest winds in the solar system, 2,575 kilometers per hour, 1,600 miles per hour. Winds moving faster than the speed of sound on Earth, tearing through an atmosphere so cold that methane freezes out of the air and falls as snow. These planets are not habitable. They are not explorable in any traditional sense. You cannot land on them. You cannot walk on them. You cannot breathe their air, or drink their water, or survive their weather. And yet they are here, right here, in the same solar system that produced the one planet where you can walk outside without a suit and not die immediately. The same solar system that made Earth with its breathable atmosphere and liquid oceans and magnetic field that shields us from solar radiation also made Venus, also made Jupiter, also made Neptune with its supersonic winds and storms that could swallow continents. That is the paradox. The solar system is not uniform. It is not fair. It did not set out to make 8 planets that humans could visit comfortably. It set out to make 8 planets, full stop, and only one of them happened to land in the narrow band of conditions where liquid water stays stable, where temperatures allow organic chemistry, where a magnetic field and an atmosphere and a moon all conspired to create something stable enough for life to start and weird enough for it to keep going. The rest of the solar system got different instructions. This is not a tour. This is an autopsy. We are going to walk through these worlds one by one, look at what makes them hostile, and figure out why they ended up that way. Not because it is comforting, because it is useful. Every planet is an experiment. Every moon is a data point. Every extreme of temperature and pressure and wind speed tells us something about the rules that govern planetary formation, atmospheric dynamics, and the physics of matter under stress. Earth is not the default. Earth is the exception. And understanding why these other worlds turned out so differently is how we figure out what made Earth possible in the first place. Some of these places are frozen, some are burning, some are spinning so fast or so slow that the concept of a day stops making sense. Some have atmospheres so thick they trap heat like an oven. Others have atmospheres so thin that standing on the surface is functionally identical to standing in the vacuum of space. One of them rains diamonds. One of them has volcanoes that erupt ice instead of lava. One of them has a storm that has been running since before your great-great-grandparents were born, and it shows no sign of stopping. We know this because we sent machines to look. Probes with cameras and spectrometers and magnetometers launched decades ago, flying for years through empty space to take a single pass by a planet we will never visit in person. Voyager, Pioneer, Galileo, Cassini, New Horizons. They flew past these worlds and sent back pictures, and the pictures told us that our solar system is stranger than we thought, more violent, more beautiful in a terrible sort of way. The kind of beauty you get from watching a forest fire from a distance. Impressive, worth studying. Absolutely not safe. And all of this is just the start. This is just the 8 major planets and their moons. We have not even touched the Kuiper belt, the scattered disk, the Oort cloud. We have not talked about the rogue asteroids or the comets that dive in from the outer dark every few decades. We have not discussed what happens when worlds collide, when moons get too close to their parent planets and tear themselves apart under tidal forces, when impacts reshape entire hemispheres in a matter of seconds. The solar system is not trying to kill you personally. It is not malicious. It is not aware of you at all. That is part of what makes it so unsettling. These worlds do not care whether you understand them, or fear them, or find them beautiful. They simply are. They exist in states that would kill you, and they have existed in those states for billions of years, long before anything on Earth developed a nervous system to process the concept of danger. So when we talk about terrifying worlds, we are not talking about monsters, we are talking about physics. Temperatures and pressures and wind speeds that sit so far outside human experience that they might as well be fictional. Except they are not fictional, they are real, they are measurable, and in some cases they are close enough that you could reach them in a human lifetime if you were willing to spend that lifetime in a spaceship. Venus is next, the planet next door, the one that looks like Earth's twin from a distance. Same size, same mass, same general position in the inner solar system. And it is hell, literally. If you were designing a hell, you would design Venus. We are going to walk through why it turned out that way, how a planet that started so similar to Earth ended up so catastrophically different, and what that tells us about the fragility of the conditions that keep our own atmosphere stable. After that, Jupiter, the king of the planets, the storm that refuses to die. And then deeper, past the rings, past the ice, out to the edge where sunlight fades and the cold becomes absolute and the planets stop looking like anything we have words for. This is the solar system. This is home, and it is more hostile than you thought. Venus is 26 million miles away at its closest approach to Earth. That is the nearest any major planet ever gets to us. Mars comes within 34 million miles on a good pass. Jupiter is never closer than 365 million. Venus is the neighbor, the planet next door. Close enough that with a powerful telescope you can watch it drift across the face of the sun during a rare transit. Close enough that some of the earliest astronomers thought it might be a sister world. Same size as Earth, give or take a few hundred miles. Same rocky composition. Same position in the inner solar system, where temperatures should allow for liquid water and breathable air and the basic conditions for life. They were wrong about all of it. Venus is not a sister world. It is a warning. A demonstration of how badly planetary evolution can go wrong when a few variables slip out of alignment. If Earth is the Goldilocks planet, the one where everything landed just right, Venus is the cautionary tale. The planet that started with similar ingredients, cooked them under slightly different conditions, and ended up with a surface hot enough to melt lead under an atmosphere that would crush you flat before the heat had a chance to finish the job. The numbers are difficult to process because they sit so far outside normal experience. The average surface temperature on Venus is 864 degrees Fahrenheit. Some measurements push it closer to 900. That is 467 degrees Celsius. For reference, lead melts at 621 degrees Fahrenheit. Zinc melts at 787. Aluminium, the metal we use to wrap leftovers, liquefies at 1221. Venus is not quite hot enough to melt aluminium, but it is well past the point where any organic molecule would break apart, where water would flash to steam instantly, where the concept of a cool shadow stops meaning anything because the entire planet is an oven, and the oven has been set to broil for the last 4 billion years. Here is the strangest part. Mercury, the closest planet to the Sun, sits at an average surface temperature of about 333 degrees Fahrenheit on the day side. Hot, yes. Uninhabitable, absolutely, but nowhere near Venus. Venus is almost 3 times hotter than Mercury, despite being nearly twice as far from the Sun. Mercury receives roughly 4 times the solar energy per square meter that Venus does. By all reasonable logic, Mercury should be the furnace and Venus should be merely unpleasant. That is not how it worked out. The difference is the atmosphere, or more precisely, the catastrophic runaway process that built Venus's atmosphere into the thickest, heaviest, most efficient heat trap in the entire solar system. Venus's atmosphere is 96.5% carbon dioxide. The rest is mostly nitrogen with traces of sulfur dioxide, carbon monoxide, water vapor, and a few noble gases that do not react with anything and have been sitting there since the planet formed. The total mass of that atmosphere is 93 times the mass of Earth's entire atmosphere. If you stood on the surface of Venus, you would not be standing in air. You would be standing at the bottom of an ocean of gas, so dense that it behaves more like a fluid than a gas. The pressure at the surface is 92 bar. In more familiar terms, that is 92 times the atmospheric pressure at sea level on Earth, roughly 1,350 pounds per square inch. To experience that kind of pressure on Earth, you would need to dive to a depth of about 3,000 feet underwater, deeper than all but a handful of submarines are rated to go, deep enough that the water around you starts to feel like it has weight and texture. On Venus, that is the air. It presses in from every direction with the same force you would feel if you were swimming half a mile below the surface of the Pacific Ocean. Except, instead of water, it is carbon dioxide. And instead of the cold dark of the deep ocean, it is hotter than a self-cleaning oven. At those temperatures and pressures, carbon dioxide stops behaving the way it does on Earth. On Earth, carbon dioxide is a gas you exhale. On Venus, it is a supercritical fluid. That is a state of matter that exists when a substance is heated and pressurized past a certain threshold called its critical point. Above that point, the distinction between liquid and gas breaks down. The substance takes on properties of both. It flows like a liquid, but fills space like a gas. The surface of Venus is covered in a supercritical sea of carbon dioxide, and that sea is dense enough that it has about 6.5% the density of liquid water. You could not swim in it, but if you dropped something heavy, it would fall more slowly than it would on Earth because the fluid around it has real resistance. The clouds above that supercritical ocean are not water, they are sulfuric acid. Concentrated sulfuric acid, the kind that will burn through skin and metal, suspended in droplets throughout Venus's upper atmosphere. The cloud deck sits between 30 and 40 miles above the surface, thick enough to reflect about 80% of the sunlight that hits the planet. That is why Venus looks so bright in Earth's sky. It is not glowing, it is just an extremely good mirror wrapped in acid. The clouds themselves are tinted yellow and brown from sulfur compounds mixed with traces of ferric chloride, phosphoric acid, and possibly solid sulfur particles. Some researchers think there might be trace amounts of nitrosyl sulfuric acid in there as well, which is a compound so reactive it does not exist naturally on Earth. For a long time, people talked about acid rain on Venus. The image was dramatic. A planet where it rains battery acid. Technically, sulfuric acid does form droplets in the upper atmosphere, and those droplets do fall, but they never make it to the surface. The heat is so intense that by the time the droplets descend below about 15 miles altitude, they evaporate completely. The sulfuric acid breaks apart into sulfur trioxide and water vapor, and those gases get pulled back up into the atmosphere by convection currents, where they recombine into sulfuric acid again and fall again in an endless loop. It does not rain on Venus, it tries to rain. The rain just burns away before it lands. The surface has not seen liquid fall from the sky in billions of years. The wind is another problem. At ground level, the air barely moves. The atmosphere is so dense and the surface so hot that convection does not work the way it does on Earth. There is no day-night temperature difference to drive wind because the greenhouse effect has erased that difference. The night side of Venus is just as hot as the day side, but high in the atmosphere, in the cloud tops, the wind screams. Winds at the upper cloud level have been clocked at speeds between 110 and 220 miles per hour. Some measurements put the peak velocity closer to 360. That is faster than a Category 5 hurricane on Earth, and it is the normal state of Venus's upper atmosphere. The entire cloud deck rotates around the planet in about 4 Earth days, even though the planet itself takes 243 Earth days to complete one rotation. The clouds lap the planet 60 times faster than the ground beneath them turns. Atmospheric scientists call this phenomenon superrotation, and they still do not fully understand what drives it. Venus spins slowly, and it spins backward. Most planets in the solar system rotate in the same direction they orbit the Sun, a leftover from the spinning disk of gas and dust that formed the solar system 4.5 billion years ago. Venus rotates the opposite way, retrograde. If you could stand on Venus and survive long enough to watch the sun rise, it would rise in the west and set in the east. One day on Venus lasts 243 Earth days. 1 year, one full orbit around the sun, takes 225 Earth days. That means a day on Venus is longer than a year on Venus. The sun rises, crosses the sky over the course of about 58 Earth days, sets, and then you wait another 58 days for it to come back. Except you would not be waiting, because you would have been dead for 57 days and 23 hours. Nobody knows for sure why Venus spins backward. The most widely accepted theory is that early in the planet's history, something large hit it at just the right angle to flip its rotation. Either that or the thick atmosphere exerts enough drag on the surface through tidal forces that over billions of years it slowly reversed the planet's spin. Either way, Venus is wrong in almost every direction you measure it. We did not know how wrong until we sent machines there. For most of human history, Venus was a mystery wrapped in clouds. Astronomers could see the planet. They could measure its size and its orbit. They could watch it move across the sun during transits and calculate its distance. But the clouds were opaque. Visible light does not penetrate them. The surface was invisible. Some early 20th century scientists speculated that Venus might be covered in oceans. Others thought it might be a swampy jungle world, hot and humid, but potentially habitable. A few suggested it was a desert. None of them guessed correctly, because none of them had any way to see through the clouds or measure the temperature below them. The first real data came from radio telescopes in the 1950s. By bouncing radio waves off Venus and measuring the return signal, astronomers were able to estimate the surface temperature. The numbers came back strange. Too hot, way too hot. At first, some researchers thought the instruments were miscalibrated. They were not. Follow-up observations confirmed it. The surface of Venus was hundreds of degrees hotter than it should be. That was the first clue that something had gone catastrophically wrong with the planet's climate. The Soviet Union sent the first probes. Venera 1 launched in 1961. It lost contact on the way and flew past Venus without returning data. Venera 2 and 3 also failed. Venera 4, launched in 1967, made it into the atmosphere and transmitted data for about an hour before the pressure crushed it. The probe had been designed to survive what scientists at the time thought Venus's atmosphere would be like. They thought the pressure might be around 10 or 15 bar. Uncomfortable, but manageable. Venera 4 was built to handle up to 25 bar as a safety margin. It died at 25 bar, still 17 miles above the surface. The pressure kept climbing. Venera 5 and 6, launched in 1969, were reinforced. They made it slightly deeper before being crushed. Venera 7, launched in 1970, was the first probe to reach the surface intact. It transmitted for 23 minutes before the heat killed its electronics. During those 23 minutes, it measured a surface temperature of 475 degrees Celsius and a pressure of 90 bar. Venera 8, launched in 1972, confirmed those numbers and survived for 50 minutes on the surface, long enough to measure light levels and determine that the sun was visible through the clouds as a dim glow. Venera 9 and 10, launched in 1975, carried cameras. They sent back the first photographs of Venus's surface, flat rocks under an orange sky. The rocks looked sharp, angular, like they had been fractured and not yet eroded. The sky looked dim, perpetual twilight, even though the sun was overhead. The images transmitted for less than an hour each before the probes failed. Later missions refined the picture. NASA's Pioneer Venusphere probes dropped 4 separate instruments into the atmosphere in 1978. The largest probe survived just under an hour on the surface. The Soviet Vega program sent balloon probes that floated in the upper atmosphere for a few days in the 1980s, measuring winds and temperature gradients and confirming that the cloud deck was sulfuric acid all the way through. The Magellan orbiter, launched by NASA in 1989, used radar to map the surface in detail, revealing a world covered in volcanic plains, deformed mountain ranges, and thousands of volcanoes. Some of the volcanoes might still be active. Magellan detected variations in sulfur dioxide levels in the atmosphere that could indicate recent eruptions, but nobody has confirmed it. No probe has survived on the surface for more than 2 hours. Most die in under an hour. The heat and pressure are just too much. Electronics fail, seals crack. Batteries drain faster than expected because the ambient temperature is so high that chemical reactions inside them speed up uncontrollably. Every lander we have ever sent to Venus has effectively been a countdown timer. You design it, you drop it, and you pull as much data as you can before it melts. The question that haunts planetary scientists is how Venus ended up this way. It did not start as a hellscape. Early in the solar system's history, Venus likely had liquid water on its surface. The planet formed from the same cloud of gas and dust that formed Earth. It ended up with roughly the same size, the same mass, the same basic composition: rock and iron, a molten core, a thin early atmosphere. For the first few 100 million years, Venus and Earth probably looked similar. 2 rocky worlds cooling off after formation, outgassing volatile compounds, building atmospheres from volcanic emissions, getting pounded by asteroids and comets left over from the solar system's assembly. Then something diverged. The leading theory is that Venus experienced a runaway greenhouse effect. Here is how it works. Early Venus had water. That water existed as vapor in the atmosphere and as liquid on the surface. Water vapor is a greenhouse gas. It traps heat. The more water vapor in the atmosphere, the warmer the planet gets. A warmer planet evaporates more water from the oceans, which puts more water vapor in the atmosphere, which traps more heat, which warms the planet further, which evaporates more water. This is a feedback loop. On Earth, the loop is kept in check by several factors. Rain removes water vapor from the atmosphere. Plants and oceans absorb carbon dioxide. Plate tectonics recycle carbon into the mantle. The system has brakes. On Venus, the brakes failed. Venus is closer to the Sun than Earth is. That means it receives more solar energy, not enough to cause a runaway on its own, but enough to start the process. Early Venus warmed up slightly more than Earth did. That extra warmth evaporated more water. The additional water vapor trapped more heat. The temperature climbed. Eventually, the oceans started to boil. Once the oceans boiled away completely, there was no liquid water left to absorb carbon dioxide from volcanic eruptions. The carbon dioxide built up in the atmosphere with nothing to remove it. Carbon dioxide is a greenhouse gas. More carbon dioxide meant more heat, which triggered more volcanic outgassing, which added more carbon dioxide. The loop locked in. At some point, Venus crossed a threshold where the process could not reverse. The water vapor in the upper atmosphere was broken apart by ultraviolet light from the sun. The hydrogen escaped into space. The oxygen either combined with surface rocks or was blown away by the solar wind. Without water, there was no way to scrub carbon dioxide from the atmosphere. The planet was left with a thick blanket of carbon dioxide, trapping every bit of solar energy that made it through the clouds. The surface heated up to the point where rocks glowed faintly in the infrared. The temperature equalized across the entire planet because the atmosphere was so thick it redistributed heat almost perfectly. Day and night, equator and poles, it all evened out to the same brutal temperature. This is the greenhouse effect at its most extreme. On Earth, the greenhouse effect is what keeps the planet warm enough for liquid water. Without it, Earth's average temperature would be around 0 degrees Fahrenheit, and the oceans would freeze. A mild greenhouse effect is essential for habitability. Venus shows what happens when the effect goes unchecked. The same mechanism that keeps Earth livable turned Venus into a pressure cooker with no release valve. The scary part is that Venus did not need much of a push to tip over the edge. The difference in solar energy between Earth's orbit and Venus's orbit is only about 25%. That is the margin. A planet slightly closer to the Sun, with slightly more water vapor in its early atmosphere and no good way to remove carbon dioxide, ends up like Venus. A planet slightly farther out, with plate tectonics and liquid oceans that can absorb carbon, ends up like Earth. The gap between habitable and hellish is narrower than anyone would like to admit. Venus also teaches us that atmospheric composition matters more than distance from the Sun. Mercury, which is even closer to the Sun than Venus, has almost no atmosphere. During the day, its surface heats up to about 800 degrees Fahrenheit. At night, it drops to -290. Mercury has extreme temperature swings, but it does not have a runaway greenhouse because it does not have the atmosphere to trap heat. Venus, farther from the Sun, is hotter than Mercury ever gets because its atmosphere is doing all the work. The lesson is clear. If you want to predict a planet's surface temperature, do not just look at how much sunlight it receives. Look at what is wrapping around it. The surface of Venus is geologically young compared to most rocky bodies. The Magellan radar maps showed relatively few impact craters, which means the surface has been resurfaced within the last few 100 million years. On a planet with no water and no plate tectonics, that resurfacing probably happened through massive volcanic eruptions. At some point in Venus's recent past, geologically speaking, the entire planet may have undergone a global volcanic event that melted and reformed huge sections of the surface. Some researchers call this a volcanic catastrophe. The evidence is scattered across the planet. Vast plains of solidified lava, pancake-shaped domes where thick lava oozed out and spread. Shield volcanoes, hundreds of them, some larger than anything on Earth. If Venus still has active volcanism, and there is some evidence it might, then the sulfur dioxide in the atmosphere is being continuously replenished. Sulfur dioxide reacts with other compounds and gets removed from the atmosphere over time. So, if it is still there in measurable amounts, something must be adding it back. The Vega balloons and later orbiters detected fluctuations in sulfur dioxide levels that could indicate eruptions happening within the last few decades. Nobody has seen an eruption directly, but the indirect evidence is sitting there in the atmospheric chemistry. Standing on Venus would not give you time to appreciate any of this. You would step out of a hypothetical lander onto a flat plain of basaltic rock under a dim orange sky. The sun would be hidden somewhere above the clouds, casting a diffuse glow that barely registers as daylight. The air around you would be thick, almost syrupy. You would feel the pressure immediately, a crushing weight pressing in from every direction. Your suit, assuming you had one capable of withstanding 92 bar, would creak and groan. The temperature would climb through the suit's insulation within seconds. You would see the rocks around you, sharp-edged and dark, maybe a distant ridge, maybe the flank of a volcano. The horizon would be closer than on Earth because Venus is slightly smaller and the thick atmosphere bends light in strange ways. You would not hear anything. The atmosphere is too thick for normal sound propagation. Everything would feel muted, distant, wrong. You would check your suit's readouts, internal temperature climbing, pressure seals holding but straining, power draining faster than expected because the heat is cooking your batteries. You would have minutes, maybe an hour if your engineers were very good and very lucky, to collect samples or take readings or do whatever you came to do. Then the suit would fail, a seal would crack, or a joint would give, or the electronics would fry. The atmosphere would rush in. At 92 bar, it would not feel like air. It would feel like being crushed by a hydraulic press while someone poured molten metal over you. You would lose consciousness almost immediately. Death would follow in seconds. The surface of Venus does not kill you slowly. It kills you fast, and it kills you completely. That is Venus. The planet next door, the one we thought might be habitable back when we could not see through the clouds. It is the single best argument against complacency when it comes to planetary atmospheres. A world that started with the same building blocks as Earth, assembled in roughly the same region of the solar system, and ended up as the most hostile major planet in the inner solar system because a few variables went wrong early and the feedback loops locked in. If Venus teaches us anything, it is that planets are not static. They evolve. Atmospheres can tip. Oceans can boil away. A climate that starts mild can spiral into something unrecognizable if the right feedback loops align. Venus is not just a cautionary tale for exoplanet scientists trying to identify habitable worlds around other stars. It is a reminder that Earth's current state is not guaranteed. Our atmosphere is balanced by processes that took billions of years to stabilize and could be disrupted by changes we are only beginning to understand. Venus is still there, still spinning slowly backward, still wrapped in acid clouds and crushing heat. And the next time you see it in the evening sky, bright and steady and beautiful, remember what it actually is. Not a sister, a warning. Now we go farther, past the asteroid belt, into the realm of storms that have been raging longer than human civilization. Jupiter is waiting, and it does not have a surface to stand on. What it has is worse. Jupiter is not a planet in the way you think of planets. It does not have a surface you could land on. It does not have ground. If you flew a spacecraft into Jupiter expecting to eventually touch down on something solid, you would just keep falling. The atmosphere would get thicker. The pressure would climb. The hydrogen around you would compress into states of matter that do not exist anywhere on Earth. Eventually, thousands of miles down, the pressure would be so intense that hydrogen stops acting like a gas and starts acting like a liquid metal. You would be crushed flat long before you reached that depth, and your spacecraft would be compacted into a ball of scrap metal the size of a marble. But you would never hit a surface. There is no bottom. Just pressure climbing forever until you reach a core that might not even be solid, just a dense soup of rock and metal and hydrogen compressed into something we do not have a good name for. That is Jupiter, the largest planet in the solar system. A ball of gas so massive it contains 2.5 times the mass of every other planet combined. You could fit 11 Earths across its diameter. You could fit over 1,300 Earths inside its volume. It is not the biggest thing in the solar system. The Sun is roughly 1,000 times more massive, but Jupiter is the biggest thing that is not a star. And if Jupiter had been about 80 times more massive, it would have been a star. It sits right on the edge, a failed star. A planet that almost made it but did not quite have enough mass to ignite fusion in its core. Instead, it just glows faintly in the infrared from leftover heat from its formation 4.5 billion years ago, radiating more energy into space than it receives from the Sun. From a distance, Jupiter looks calm, bands of color, stripes of white and brown and orange wrapping around the planet in neat parallel lines. The photos make it look almost orderly, structured. The bands are clouds, organized into zones and belts by the planet's rapid rotation. Jupiter spins faster than any other planet in the solar system. One full rotation takes just under 10 hours. 10 hours for an object 88,000 miles across to spin all the way around. That is absurdly fast. The equator is moving at roughly 28,000 miles per hour. For comparison, Earth's equator moves at about 1,000 miles per hour. Jupiter is spinning so fast that it bulges at the equator. The planet is not a sphere. It is visibly flattened, wider across the middle than it is from pole to pole. That spin is what drives the bands. As the planet rotates, the atmosphere gets stretched out into horizontal stripes. Warm gas rises in the bright zones. Cool gas sinks in the dark belts. The whole system is driven by heat from below and the Coriolis effect from the planet's rotation. The boundaries between zones and belts are not calm borders. They are shear zones where winds moving in opposite directions at hundreds of miles per hour grind past each other. Those shear zones are where the storms form, and Jupiter has storms like nothing else in the solar system. The most famous one has been running for at least 150 years. Maybe longer, maybe centuries longer. We do not know for sure because we only started keeping detailed records of Jupiter in the 1800s, but there are sketches from the 1660s that might show the same storm. Robert Hooke in 1664 and Giovanni Cassini in 1665 both drew a large spot on Jupiter's surface. The drawings are crude, the descriptions are vague. It is possible they were seeing the same storm we see today. It is also possible that storm died and another one started later in the same region. We will never know. What we do know is that by 1831, astronomers were regularly observing a massive oval storm in Jupiter's southern hemisphere, and that storm has not stopped since. We call it the Great Red Spot. The name is straightforward. It is great, meaning large. It is red, or at least reddish-orange, and it is a spot, a discrete feature you can point to and track across the planet's face as Jupiter rotates. The Great Red Spot is an anticyclone. That means it rotates in the opposite direction of a typical low-pressure system. On Earth, hurricanes in the northern hemisphere spin counterclockwise. In the southern hemisphere, they spin clockwise. The Great Red Spot is in Jupiter's southern hemisphere, and it spins counterclockwise, the opposite of what a normal storm in that hemisphere would do. It is a high-pressure system, not a low-pressure one. Think of it less like a hurricane and more like a massive high-pressure dome that has been locked in place for over a century, spinning on its axis and refusing to dissipate. The size is difficult to wrap your head around. As of 2017, the most recent precise measurements put the Great Red Spot at roughly 16,350 kilometers across. That is about 10,160 miles. For reference, Earth's diameter is 12,742 kilometers. The storm is 1.3 times wider than the entire planet you are standing on. If you placed Earth next to the Great Red Spot, the storm would swallow it with room to spare. It used to be bigger. In 1879, when the Voyager probes flew past Jupiter, the Great Red Spot measured roughly 25,000 kilometers across. It has shrunk by about 1/3 since then. Some years it shrinks faster than others. Some years it seems to stabilize. Nobody knows why it is shrinking or whether it will continue to shrink until it disappears entirely. Some models suggest the storm could collapse within a few decades. Others say it could stabilize at a smaller size and keep running for centuries. We are watching in real time as one of the solar system's most iconic features slowly fades, and we do not have a good explanation for why it is happening. The winds inside the storm are ferocious. The outer edge of the Great Red Spot clocks wind speeds of up to 680 kilometers per hour. That is about 425 miles per hour. The fastest wind speed ever recorded on Earth was 253 miles per hour during Tropical Cyclone Olivia in 1996. The Great Red Spot's edge winds are nearly twice that fast, and those winds have been blowing continuously for longer than the United States has existed as a country. Here is the strange part. The center of the storm is calm, dead calm. Juno, NASA's Jupiter orbiter, flew directly over the Great Red Spot in July 2017 and measured wind speeds at different altitudes and different positions within the storm. The data showed that the fastest winds are concentrated in a narrow band around the edge of the oval. Inside that band, the winds drop off sharply. At the very center of the storm, the air is nearly still. It is the eye of the hurricane on a scale that makes terrestrial hurricanes look like dust devils. The difference is that hurricanes on Earth are low-pressure systems with calm centers because air is sinking. The Great Red Spot is a high-pressure system. The calm center is caused by something else, possibly the storm's rotation creating a centrifugal barrier that prevents the outer winds from penetrating inward. The color is a mystery. The Great Red Spot is not uniformly red. It is more of a rust orange or salmon pink, depending on the lighting and the year you observe it. Some years it looks darker. Some years it fades to almost white before reddening again. Nobody knows what causes the color. The leading theories suggest it might be chemicals brought up from deeper in Jupiter's atmosphere. Compounds that react with sunlight and turn red. Ammonia is a candidate. Sulfur compounds are another. Some researchers think the color might come from organic molecules, complex carbon-based compounds formed when simpler molecules are broken apart by ultraviolet light and reassemble into chromophores, molecules that absorb certain wavelengths of light and reflect others. The problem is that we cannot sample the storm directly. No probe has ever descended into Jupiter's atmosphere and survived long enough to send back detailed chemical data from inside the Great Red Spot. Everything we know comes from remote sensing, from spectroscopy and imaging, and the resolution is not high enough to definitively identify the compounds responsible for the color. We know the storm is red. We do not know why. Juno changed the game in 2016. Before Juno, everything we knew about the Great Red Spot came from flybys. Voyager 1 and 2 in 1979, Galileo in the 1990s, Cassini on its way to Saturn in 2000, New Horizons on its way to Pluto in 2007. These missions gave us incredible images and some atmospheric data, but they were snapshots, quick passes. Juno was designed to stay. It entered orbit around Jupiter in July 2016 and has been circling the planet ever since in a highly elliptical polar orbit that brings it skimming within a few thousand kilometers of the cloud tops once every 53 days. On July 11, 2017, Juno flew directly over the Great Red Spot. Its instruments were pointed straight down into the storm. What they found shocked everyone. The storm is deep, not surface deep, not 100 kilometers deep, 300 to 500 kilometers deep. That is the distance from the cloud tops down to the base of the storm, where the winds finally die out and the atmosphere below continues undisturbed. For context, Earth's atmosphere is about 100 kilometers thick from sea level to the edge of space. The Great Red Spot extends 3 to 5 times deeper than Earth's entire atmosphere. Before Juno, most models assumed the storms on Jupiter were relatively shallow. The thinking was that the atmosphere was layered, with weather confined to the upper few dozen kilometers and the deeper layers remaining calm. Juno's gravity and microwave measurements showed that was wrong. The storms on Jupiter are not surface phenomena. They are deep, rotating columns of atmosphere that extend hundreds of kilometers down into the planet. The Great Red Spot is not just a storm, it is a vertical structure, a cylinder of rotating gas anchored deep below the visible clouds. That depth is what gives the storm its longevity. On Earth, hurricanes die when they make landfall or when they move over cold water. They need a steady supply of warm, moist air to keep running. Cut off that supply, and the storm collapses within days. The Great Red Spot does not have that problem. It is floating in an ocean of atmosphere with no land to hit and no cold water to cross. The heat comes from below, from Jupiter's interior, which is still radiating leftover energy from the planet's formation. The storm can keep pulling energy from that deep heat reservoir indefinitely. Add in the fact that the storm is embedded in a jet stream, a fast-moving river of wind that holds it in place and feeds it energy, and you have a system that can run for centuries without external intervention. The storm is also a predator. Juno and earlier missions observed smaller storms being pulled into the Great Red Spot and torn apart. Jupiter's atmosphere is full of smaller vortices, white ovals and brown barges and cyclones of various sizes. When one of these smaller storms drifts too close to the Great Red Spot, the larger storm's gravity and wind shear rip it apart. The fragments get absorbed into the Great Red Spot, possibly feeding it, possibly contributing to its longevity. The storm eats its neighbors. It has been doing this for at least 150 years, maybe longer, and it shows no sign of stopping. There are other storms on Jupiter. Lots of them. The Great Red Spot is just the most famous. In 2000, 3 smaller white ovals merged together in Jupiter's southern hemisphere to form a new storm called Oval BA. For a while, it was white. Then, in 2006, it turned red. Astronomers started calling it Red Spot Junior. It is about half the size of the Great Red Spot, still larger than Earth, still running with wind speeds over 300 miles per hour. In 2008, Red Spot Junior passed very close to the Great Red Spot. The two storms did not merge. They bounced off each other like billiard balls, their rotation creating a repulsive force that kept them separated. Jupiter's poles are even stranger. For decades, nobody knew what the poles looked like. All the major flybys approached Jupiter from the equatorial plane, the same plane where the planet's moons orbit, because that is the easiest trajectory from Earth. The poles were hidden, always angled away from the cameras. Juno was the first mission to get a clear look. The poles are covered in cyclones, not 1 or 2, dozens. At the North Pole, there is a central cyclone roughly the size of Texas, surrounded by a ring of 8 smaller cyclones arranged in an almost perfect octagon. Each of those smaller cyclones is still the size of a large terrestrial hurricane. They sit there, locked in formation, spinning in place. The South Pole has a similar arrangement, with a central cyclone surrounded by 5 smaller ones in a pentagonal pattern. Nobody predicted this. None of the models suggested Jupiter's poles would organize themselves into geometric patterns of storm systems. The prevailing assumption was that the poles would be chaotic, with storms forming and dissipating randomly. Instead, they are structured, stable, locked into configurations that have persisted for at least as long as Juno has been observing them. The mechanism that keeps them in place is still being worked out, but it likely involves the same balance of forces that holds the Great Red Spot together: rotation, wind shear, and pressure gradients, creating a stable equilibrium that resists disruption. Jupiter's magnetic field is another problem. The planet's field is enormous, roughly 20,000 times stronger than Earth's. That field is generated by the movement of liquid metallic hydrogen deep inside the planet. Jupiter is essentially a dynamo, a spinning ball of electrically conductive fluid that produces a magnetic field strong enough to trap charged particles from the solar wind in massive radiation belts. Those belts extend millions of kilometers into space, far enough to engulf some of Jupiter's moons. The radiation is lethal. If you flew a spacecraft through Jupiter's radiation belts without shielding, the electronics would fry in minutes. Human tissue would fare worse. The charged particles would tear through cells, breaking DNA, destroying tissue, causing radiation sickness so severe that death would follow within hours, even with medical intervention. The inner moons, Io and Europa, orbit inside those belts. Their surfaces are constantly bombarded with high-energy particles. Io's surface is the most volcanically active place in the solar system, partly because of tidal heating. But the radiation environment around it is so intense that any probe sent there has to be heavily shielded just to survive the flyby. Juno was designed to handle this. Its electronics are housed in a titanium vault, a box with walls nearly a centimeter thick that shields the sensitive instruments from radiation. Even with that protection, Juno's orbit is carefully planned to minimize time spent in the most intense parts of the radiation belts. The spacecraft dips in close to Jupiter once every 53 days, gathers data for a few hours, then swings back out to a safer distance. It is threading a needle, getting close enough to take measurements without staying long enough to be destroyed. The data Juno has sent back is rewriting textbooks. We now know that Jupiter's winds extend thousands of kilometers below the cloud tops, far deeper than anyone expected. We know that the planet's magnetic field is lopsided, stronger in the northern hemisphere than the southern, and that it is changing over time in ways we do not fully understand. We know that the interior of the planet is not as neatly layered as the old models suggested. The core is not a distinct solid ball. It is diffuse, possibly mixed with lighter elements, spread out over a larger volume than previous models predicted. Jupiter is messier on the inside than we thought. The storms are the most visible part of that mess. The Great Red Spot is just the biggest, the longest-lived, the most obvious. But the entire planet is covered in storms, bands of clouds racing past each other at hundreds of miles per hour. Vortices spinning off from jet streams, merging, splitting apart, being torn to shreds by wind shear. Lightning storms crackling through the upper atmosphere, with bolts thousands of times more powerful than anything on Earth. The whole planet is a turbulent mess of weather systems stacked on top of each other, driven by heat from below and rotation from the planet's absurdly short day. If you could somehow survive in Jupiter's upper atmosphere, hovering in a balloon or a glider at the altitude where the pressure is about 1 bar, roughly the same as sea level on Earth, you would see something like a perpetual tornado. The sky would be filled with clouds moving in every direction. The horizon would curve sharply because Jupiter is so large. The sun would be smaller and dimmer than it appears from Earth, about 1/27th as bright, casting a pale light that makes everything look faint. The clouds below you would stretch out to infinity, bands of orange and white and brown disappearing into the haze. Above you, thin, high-altitude ammonia clouds, possibly sulfur compounds giving them color. The air would smell like ammonia if you could smell it without dying. The temperature at that altitude would be around -110 degrees Celsius, cold enough to freeze carbon dioxide. You would not stay there long. Jupiter's atmosphere is not stable the way Earth's is. There is no surface to provide a reference, no ground to anchor you. You would be floating in a sea of gas that extends down for thousands of kilometers, and below a certain depth, that gas becomes a liquid, and below that, a strange metallic fluid that does not exist anywhere else in the solar system. If your balloon lost altitude, you would fall, and you would keep falling until the pressure crushed you or the heat boiled you, or both. There is no landing, just descent into oblivion. Jupiter is a demonstration of what happens when you scale up weather to planetary proportions. On Earth, the biggest hurricanes last a few weeks. On Jupiter, storms last centuries. On Earth, wind speeds top out around 200 miles per hour. On Jupiter, they hit 400 and keep climbing. On Earth, the atmosphere is a thin shell a few dozen kilometers thick. On Jupiter, the atmosphere is the planet. There is no distinction. The gas goes down until it stops being gas and turns into something else, and that process happens over thousands of kilometers. You cannot think of Jupiter as a planet with an atmosphere. You have to think of it as an atmosphere with a core buried somewhere deep inside. The Great Red Spot is not an anomaly, it is a window into what Jupiter is. A storm that has outlasted empires, spinning in place, eating smaller storms, refusing to die. It is the most visible piece of a planet that is, from top to bottom, nothing but chaos held together by gravity and rotation. And it is shrinking. One of the most stable features in the solar system, a storm that has been observed for over a century, is getting smaller year by year. Nobody knows why. Nobody knows if it will stop shrinking or keep going until it collapses completely. If the Great Red Spot dies, it will be the first time in recorded history that Jupiter has not had a giant red storm in its southern hemisphere. It will change the face of the planet, and it will raise new questions about what keeps these storms stable in the first place. If a storm that has run for centuries can suddenly fail, what does that tell us about the dynamics of Jupiter's atmosphere? What does it tell us about the long-term stability of weather systems on gas giants? We do not know yet. We are still watching. Juno is still in orbit. Every 53 days, it dips close, gathers data, and sends it back. And every time it does, we learn something new about the monster in the outer solar system. Next, we head to a moon. Not one of Jupiter's moons, though those are strange enough. Saturn's moon, the one with lakes and rivers and rain, the one that looks like Earth if Earth were frozen and dipped in liquid methane. Titan is waiting, and it is not what you expect. Titan is the second largest moon in the entire solar system. Only Ganymede, one of Jupiter's collection, is bigger, and even then Titan is only about 2% smaller. That makes Titan larger than the planet Mercury, larger than Earth's moon, larger than anything you would expect to call a moon. It is 5,150 kilometers across, a world in its own right, orbiting Saturn at a distance of about 1.2 million kilometers. That is roughly 3 times farther than the moon orbits Earth. From Titan's surface, Saturn would fill a significant chunk of the sky, hanging there like a ringed painting, silent and enormous. Titan was discovered on March 25, 1655, by a Dutch astronomer named Christian Huygens. He was using a telescope he built himself, a refracting telescope with a focal length of over 3 meters, mounted on a homemade stand in his backyard. He pointed it at Saturn and saw a faint dot moving near the planet. He tracked it over several nights and confirmed it was a moon. For a long time, it was just called Saturn's moon, the only one anyone knew about. Eventually, as more moons were discovered around Saturn, John Herschel suggested naming them after the Titans from Greek mythology. The name stuck. Titan, the largest of Saturn's moons, named after the beings who came before the gods, the old powers who were overthrown and imprisoned in the underworld. The name turned out to be weirdly appropriate. Titan is old, ancient, a relic from the early solar system, barely changed since the planets finished forming, and it has been hiding something under its surface the entire time. For centuries, Titan was just a dot in telescopes. Astronomers could measure its size and its orbit, but the surface was invisible. The moon was wrapped in a thick haze that blocked all visible light. Early observers noted that Titan appeared orange or reddish, but they could not see any details. The haze was too thick. Some speculated that Titan might have an atmosphere, which would be unusual for a moon, but they had no way to confirm it. The confirmation came in 1944, when Gerard Kuiper, an astronomer working at McDonald Observatory in Texas, used spectroscopy to analyze the light reflecting off Titan. He detected methane, not just traces of it, a significant amount, enough that it had to be coming from an atmosphere. That made Titan the first moon in the solar system confirmed to have an atmosphere. Not a thin wisp of gas like the trace exosphere around Earth's moon. A real atmosphere, thick enough to block light, thick enough to support weather. The next big leap came in the late 1970s and early 80s when Voyager 1 flew past Saturn. Voyager 1's cameras captured the first close-up images of Titan in November 1980. They showed a featureless orange ball. The haze was so thick that even from close range, the spacecraft could not see the surface. But Voyager's instruments could measure other things. They measured the atmosphere's composition, they measured its pressure, they measured its temperature. The data came back strange. Titan's atmosphere is 95% nitrogen. Nitrogen, the same gas that makes up 78% of Earth's atmosphere. The remaining 5% is mostly methane, with traces of hydrogen, ethane, propane, acetylene, and other hydrocarbons. The surface pressure is 1.6 bars. That is 1.6 times the atmospheric pressure at sea level on Earth. Stand on Titan and you would feel slightly more pressure than you feel standing on a beach. Not enough to crush you, just enough to notice if you were paying attention. The atmosphere extends upward for 600 kilometers, far higher than Earth's, because Titan's gravity is weaker. The escape velocity is lower. The atmosphere puffs out farther before thinning into space. That thickness is what creates the haze. High in the atmosphere, ultraviolet light from the sun breaks apart methane molecules. The fragments recombine into more complex hydrocarbons, long-chain molecules that clump together into tiny particles. Those particles scatter light, creating a thick orange smog that blankets the entire moon. The process is similar to smog formation in polluted cities on Earth, except on Titan it is happening naturally, constantly, across the entire atmosphere. The result is that from space, Titan looks smooth and featureless, a hazy orange orb with no visible surface detail. The surface temperature is -290 degrees Fahrenheit, -179 Celsius, 94 Kelvin. That is cold enough that water ice stops behaving like ice and starts behaving like rock. On Titan, water is bedrock. Mountains are made of it. The surface is made of it. It is as hard as granite and just as permanent. Meanwhile, methane and ethane, which are gases on Earth, are liquids on Titan. They fill lakes, they flow in rivers, they evaporate into the atmosphere, form clouds, and fall as rain. That is the punchline. Titan has weather, not the thin, wispy clouds you sometimes see on Mars, real weather. A methane cycle that mirrors Earth's water cycle almost exactly. Methane evaporates from lakes on the surface. It rises into the atmosphere as vapor. It cools and condenses into clouds. The clouds drift across the landscape. When conditions are right, it rains. Liquid methane falls from the sky, hits the surface, and flows downhill, carving channels and gullies and drainage networks into the ice bedrock. The methane collects in low-lying areas, forming rivers and lakes and seas. Then it evaporates again, and the cycle repeats. For decades, this was all theoretical. Voyager proved Titan had an atmosphere. Spectroscopy showed the presence of methane. Models predicted lakes and rain. But nobody could see the surface to confirm it. The haze was too thick for visible light cameras. Infrared could penetrate slightly, but not well enough to show detail. Radar was the only option. Radar waves can punch through the haze and bounce off the surface, giving you a map of the terrain below. In 1997, NASA and the European Space Agency launched Cassini-Huygens, a joint mission to Saturn. Cassini was the orbiter, designed to spend years circling Saturn and studying its moons. Huygens was a probe, built to detach from Cassini, descend through Titan's atmosphere, and land on the surface. The mission took 7 years to reach Saturn. On December 25, 2004, Huygens separated from Cassini and began its approach to Titan. On January 14, 2005, it entered Titan's atmosphere. The descent took 2.5 hours. Huygens had no propulsion. It was a ballistic probe, riding a heat shield through the upper atmosphere, then deploying parachutes to slow its fall. As it descended, it took measurements: temperature, pressure, wind speed, chemical composition, and it took pictures, lots of pictures. The images showed something nobody had quite expected: river channels, networks of them, branching and merging, carving through the surface like drainage systems on Earth. Dark patches that looked like lakes or seas, bright highlands that could be mountains or ridges, and a surface texture that looked wet, or at least recently wet, like mud or sand that had been shaped by flowing liquid. Huygens landed in a relatively flat region near Titan's equator. The landing site was named the Huygens Landing Site because astronomers are not always creative with names. The probe hit the surface gently, sinking slightly into what felt like wet sand or loose gravel. It transmitted data for about 90 minutes before its batteries died. During those 90 minutes, it sent back the first photograph ever taken from the surface of a moon in the outer solar system. The image shows a flat plain covered in rounded rocks. The rocks are made of water ice, frozen harder than stone. Between the rocks, the ground is smooth, possibly covered in a layer of fine hydrocarbon sand or frost. The sky is a dim orange, lit by sunlight filtered through hundreds of kilometers of haze. The horizon is visible in the distance, flat and empty. It looks eerily like Earth. A riverbed on Earth after a flood has passed, leaving behind smooth stones and wet sand, except the stones are ice and the wet sand is methane residue and the temperature is 290 degrees below zero. Cassini kept flying. Over the next 13 years, the orbiter made over 100 close flybys of Titan, using radar to map the surface in detail. The maps revealed what Huygens had hinted at. Titan's surface is covered in lakes and seas, concentrated near the poles. The largest body of liquid is Kraken Mare, a sea in Titan's northern hemisphere, roughly the size of the Caspian Sea on Earth. It is filled with liquid methane and ethane, possibly mixed with dissolved nitrogen. The depth is unknown. Radar cannot penetrate liquid hydrocarbons well enough to measure the bottom. Some estimates put the depth at over 300 meters. Others suggest it could be shallower, maybe 100 meters in most places. Either way, it is deep enough to be a sea by any reasonable definition. There are smaller lakes scattered around the northern polar region. Lishaya Ma, Punga Ma, dozens of smaller unnamed lakes, some only a few kilometers across. The southern hemisphere has fewer lakes, but it has something else. Dry lake beds, empty basins with smooth flat floors and raised shorelines, exactly what you would see if a lake had evaporated or drained away. Titan's climate is seasonal. The Moon takes 29.5 Earth years to orbit Saturn, and Saturn takes 29.5 years to orbit the Sun. That means Titan's seasons last about 7 Earth years each. During Titan's northern summer, the northern lakes fill up. During the southern summer, the southern hemisphere gets more rainfall and the southern lake beds start to fill. The liquid migrates back and forth across the Moon over the course of decades, following the sunlight. Cassini also spotted something else. River channels hundreds of kilometers long, carved into the ice bedrock, leading from highland regions down into the lowland seas. Some of these channels are dry now, others might have liquid flowing through them during rainstorms. Titan gets rain, but not constantly. The rain is sporadic, seasonal, tied to atmospheric conditions that shift over years. When it does rain, it pours. Models suggest that Titan's rain comes down in large drops, bigger than raindrops on Earth, because the thick atmosphere and low gravity allow the drops to grow larger before falling. The rain hits the surface and flows downhill fast, carving channels and gullies in a matter of hours or days. The erosion patterns on Titan look almost identical to erosion patterns on Earth. Dendritic drainage networks, the branching tree-like patterns you see in river systems. Alluvial fans, the spreading deposits of sediment where rivers slow down and drop their load. Dry riverbeds with smooth polished floors where liquid has flowed recently enough to erase the rough texture. If you showed a geologist a radar image of Titan's surface without telling them where it came from, they might guess it was from Earth. The processes are the same. Liquid evaporates, forms clouds, falls as rain, flows downhill, carves channels, deposits sediment. The only difference is the liquid is methane instead of water, and the bedrock is ice instead of stone. Beneath the surface, things get stranger. Cassini's gravity measurements revealed that Titan has a subsurface ocean, not a methane ocean, a water ocean. Liquid water, mixed with salts, sitting 35 to 50 miles below the icy crust. The ocean is probably in direct contact with a rocky core at the bottom and the ice shell at the top. That means there are two completely separate liquid systems on Titan. Methane lakes and rivers on the surface, and a salty water ocean hidden below. The subsurface ocean was confirmed by analyzing radio signals from the Huygens probe during its descent. As Huygens fell, it transmitted a radio signal back to Cassini. The signal had to pass through Titan's atmosphere and then travel through space to the orbiter. By measuring tiny shifts in the signal's frequency, scientists could detect how Titan's gravitational field was affecting the probe. The data showed that Titan's interior is not rigid. It flexes slightly as Saturn's gravity pulls on it during the Moon's orbit. That flexing only makes sense if there is a layer of liquid somewhere inside. A solid ice shell all the way down to the core would not flex. A shell with a liquid layer underneath would. The best fit to the data is an ocean roughly 100 kilometers thick, sitting under an ice crust about 50 kilometers thick. That ocean might be in contact with the rocky core, and if it is, there could be hydrothermal vents. Hot water, heated by tidal forces or radioactive decay in the core, rising through cracks in the rock and mixing with the cold ocean above. On Earth, hydrothermal vents are oases of life in the deep ocean. They provide heat and chemical energy in an environment that would otherwise be lifeless. If Titan has hydrothermal vents, the subsurface ocean might be habitable, not pleasant, not easy, but chemically active enough to support some form of metabolism if the right molecules are present. The surface chemistry is equally strange. Cassini detected organic molecules in Titan's atmosphere, lots of them: methane, ethane, propane, acetylene, benzene, hydrogen cyanide, cyanoacetylene. These are the building blocks of more complex chemistry. On Earth, similar compounds are precursors to amino acids, the molecules that form proteins. Laboratory experiments have shown that if you take a mixture of gases like those in Titan's atmosphere, add energy in the form of ultraviolet light or electrical discharges, and let the reactions run, you end up with more complex organic molecules. Some of those molecules are biologically relevant. Not life, not even close, but the raw materials that could, under the right conditions, assemble into something more interesting. Titan's surface is covered in these organic molecules. The haze particles that form in the upper atmosphere eventually fall to the surface, accumulating over billions of years into a layer of organic-rich sediment. Some estimates suggest the layer could be hundreds of meters thick in places. It is essentially a frozen chemical library, a record of 4.5 billion years of atmospheric chemistry, sitting on the surface waiting to be studied. If you could scoop up a handful of Titan's surface material and bring it back to a lab, you would find a complex mixture of hydrocarbons and nitriles and other organic compounds, some of which might be molecules we have never seen before. The question that keeps coming up is whether Titan could support life. Not life as we know it, because the surface is far too cold for water-based biochemistry. Water is frozen solid. Cell membranes, as we understand them, would not work. DNA would not function. Proteins would not fold. But there are theoretical proposals for alternative biochemistries that could work in liquid methane. One idea, floated by a team of researchers at Cornell, is that you could have cell membranes made of nitrogen-based compounds called azotosomes. These would be flexible at Titan's temperatures and could enclose a cell-like structure filled with liquid methane instead of water. The chemistry inside would be completely different from Earth life, but it would still be chemistry. Molecules reacting, storing energy, self-replicating. Nobody has found any evidence of life on Titan, not in the data from Cassini, not in the images from Huygens. The surface looks barren. The lakes are empty of any obvious biology. The atmosphere shows no chemical imbalances that would suggest metabolism. But the absence of evidence is not evidence of absence, and Titan has only been studied in detail for a couple of decades. We have looked at a tiny fraction of the surface up close. We have not sampled the lakes. We have not drilled into the ice to reach the subsurface ocean. We have barely scratched the surface. NASA is planning to go back. In 2027 or 2028, the agency will launch a mission called Dragonfly. Not an orbiter, not a lander, a rotorcraft, a drone with 8 rotors designed to fly through Titan's thick atmosphere, land at multiple sites, collect samples, and take off again. The mission is planned to last at least 3 years, with Dragonfly hopping from site to site, covering hundreds of kilometers, visiting lakes, mountains, impact craters, and dune fields. The thick atmosphere and low gravity make flying on Titan easier than flying on Earth. The air is dense enough to provide plenty of lift, and the gravity is weak enough that you do not need much power to stay aloft. Dragonfly will take advantage of that, spending more time in the air than on the ground, moving across the landscape faster than any rover could. Dragonfly's primary goal is to study Titan's chemistry. It will land near the equator, in a region called the Shangri-La Dune Field, where Cassini's radar detected vast stretches of hydrocarbon sand shaped into linear dunes hundreds of kilometers long. From there, it will fly to Selk Crater, an impact site about 80 kilometers away, where liquid water from the subsurface might have been exposed briefly after the impact, mixing with the organic rich surface material. That mixing event, if it happened, would have created a natural laboratory for prebiotic chemistry. Dragonfly will analyze the chemistry in and around the crater, looking for complex organic molecules, looking for anything that might tell us how far the chemistry on Titan has progressed towards biology. The mission will also search for signs of current or past life, though the odds are long. If there is life on Titan, it is probably not on the surface. The surface is too cold, too hostile, too exposed to radiation. If life exists, it is more likely in the subsurface ocean, where liquid water and chemical energy might be available. Dragonfly cannot reach the ocean. The ice shell is too thick. But the rotorcraft can sample the surface, analyze the organic compounds, and look for chemical signatures that might hint at biological processes happening below. Standing on Titan would be surreal. The gravity is about 1/7 of Earth's. You would weigh 14% of what you weigh here. Jump, and you would hang in the air longer than feels natural. Walk, and you would have to relearn how to move, because every step would carry you farther than you expect. The ground beneath you would be frozen water ice, hard as concrete, covered in a layer of fine orange powder made of hydrocarbon particles that have drifted down from the haze over billions of years. The sky would be orange, dim, like late twilight even at noon. The sun would be a faint disk behind the haze, barely brighter than a full moon on Earth. Saturn, if it were in the sky, would be massive, filling a large chunk of the view, its rings edge-on or fully visible depending on the season. The air would be thick. You would feel it when you moved, a slight resistance, like wading through water, but much gentler. The pressure would be slightly higher than what you are used to, but not enough to hurt. The temperature would kill you in seconds. -290 Fahrenheit is cold enough that exposed skin would freeze almost instantly. Your breath would condense into ice crystals and fall to the ground. Any moisture in your lungs would freeze. You would need a heated suit, heavily insulated, with active warming systems to keep your core temperature stable. The suit would need to be pressurized, not because the external pressure is too low, but because you still need breathable air, and Titan's atmosphere is poison. Nitrogen is inert, but methane is not. Breathe it in, and it displaces oxygen. You would suffocate. If you stood near one of the northern lakes, you would see liquid methane stretching out to the horizon, dark and still, reflecting the orange sky. The surface would be smooth, almost glassy, because methane has very low viscosity and very low surface tension. Waves would be small, gentle ripples rather than the large swells you see on Earth's oceans. The shore would be made of ice, possibly covered in a slush of methane-soaked hydrocarbon sediment. No sound except the faint hiss of wind through the haze, the crunch of your boots on frozen ground, the hum of your suit's heating system. There would be no life visible, no plants, no animals, no movement except the slow drift of haze particles falling from the sky and the occasional gust of wind stirring the surface of the lake. It would feel empty, dead. But chemically, it would be one of the most active places in the solar system. Every breath of that methane-rich atmosphere, every drop of liquid in that lake, every grain of that organic sediment would be a molecule away from something more complex. Titan is not alive. But it is not quite dead either. It is waiting. 4.5 billion years of chemistry piling up on the surface, in the lakes, in the atmosphere, waiting for the right conditions or the right catalyst to push it one step farther. That is the paradox of Titan. It looks like Earth. It has weather like Earth. It has lakes and rivers and rain and erosion just like Earth. But it is built from completely different materials, running at completely different temperatures, governed by completely different chemistry. It is a mirror of our world, distorted by cold and distance into something that feels familiar and alien at the same time. An Earth analog in a cryogenic nightmare, where water is stone and methane is rain, and the only ocean is buried under miles of ice. Titan is not trying to kill you the way Venus is. It is not crushing you like Jupiter. It is just cold, brutally, lethally cold, and thick with organic chemistry that refuses to do anything interesting because the temperature is too low for the reactions to proceed. It is a frozen laboratory, a planetary scale experiment in what happens when you take Earth's water cycle and run it with methane instead. When you take Earth's chemistry and freeze it at -290 degrees and let it sit for 4 billion years, and it is still running. The methane cycle is still turning, the lakes are still evaporating, the clouds are still forming, the rain is still falling. Somewhere on Titan right now, it is raining liquid methane onto a frozen plain of water ice, and that rain is carving new channels into the surface, exactly the way rain carves channels on Earth. The chemistry is strange, but the physics is familiar. Titan is not Earth, but it is the closest thing to Earth that exists anywhere else in the solar system. Next, we leave the realm of familiar moons and head to the edge of the ice giants. Uranus, the planet that spins on its side, wrapped in a frozen atmosphere, hiding secrets we have only glimpsed once. We are going deeper now, farther from the sun, into regions where the rules change and the planets stop making sense in any comfortable way. Uranus is waiting, tilted at an angle that should not exist, and nobody can tell you why. Uranus spins on its side. That is the first thing you need to know about it, and the most important thing. Not slightly tilted like Earth, which leans at a comfortable 23.5 degrees and gives us normal seasons where summer and winter trade places in a rhythm everyone understands. Uranus is tilted 97.77 degrees, almost a perfect right angle. The planet is lying down in its orbit, rolling through space like a barrel tumbling end over end, with its north pole pointed almost directly at the sun for half of its 84-year orbit, and its south pole pointed at the sun for the other half. Picture a spinning top that someone kicked over. Now imagine that top is 31,000 miles across, wrapped in a frozen atmosphere of hydrogen and methane, sitting nearly 2 billion miles from the sun, and it has been spinning in that knocked-over position for the last 4.5 billion years. That is Uranus, the planet that broke the rules and never bothered to fix itself. The tilt changes everything. On Earth, the poles get continuous daylight in summer and continuous darkness in winter, but only for a few months at most, and only in the extreme Arctic and Antarctic. On Uranus, each pole gets 42 years of continuous sunlight, followed by 42 years of continuous darkness. 42 years, that is longer than most human beings have been alive. If you were born during the start of Uranus's northern summer, you would be middle-aged by the time the sun finally set at the North Pole, and then it would stay dark for another 42 years. Your entire retirement would pass in polar night. During those long summers, the sun does not rise and set. It just circles the sky, hovering near the horizon, making a slow spiral that takes 17 hours to complete, because that is how fast Uranus rotates. One day on Uranus is 17 hours and 14 minutes. The sun wheels around the pole in a flat circle, never climbing high, never dipping below the horizon, just endlessly circling for decades. Then, as the planet moves along its orbit, the sun starts to sink. Slowly. Over the course of years, it drops lower and lower toward the horizon until finally, after 42 years of daylight, it sets, and it stays set for the next 42 years. Meanwhile, the equator experiences something closer to a normal day-night cycle, but stretched and distorted. For half the orbit, the equator is in twilight. The sun skims along the horizon, rising and setting every 17 hours, but never climbing high into the sky. For the other half of the orbit, the equator is in relative brightness, with the sun making longer arcs across the sky. But even then, it is dim. Uranus is 19 astronomical units from the sun. 1 astronomical unit is the distance from the Earth to the sun, about 93 million miles. Multiply that by 19 and you get a planet so far out that sunlight arrives nearly 400 times weaker than it does on Earth. Standing on Uranus, if Uranus had a surface to stand on, which it does not, the sun would look like a very bright star. Brighter than anything else in the sky, yes, but small, distant, faint, not the blazing disk you see from Earth, a pinpoint of light that barely registers as warmth. The temperature reflects that distance. Uranus is cold, brutally cold. The minimum temperature recorded in its atmosphere is 49 Kelvin. That is minus 224 degrees Celsius, minus 371 Fahrenheit. Cold enough that almost every gas you can think of would freeze solid. Oxygen would be ice, nitrogen would be ice, carbon dioxide would be a solid block. Methane, which makes up a small percentage of Uranus's atmosphere, is right on the edge of freezing. It condenses into clouds high in the atmosphere, giving the planet its pale blue color, and those clouds are made of methane ice crystals drifting through hydrogen and helium. Here is the strangest part. Uranus is colder than Neptune. Neptune is farther from the sun. Neptune sits about 30 astronomical units out, half again as far as Uranus. By every reasonable expectation, Neptune should be the colder planet. It is not. Neptune's atmosphere averages around 72 Kelvin. Uranus averages 59 Kelvin. Uranus, closer to the sun, is about 13 degrees colder than Neptune. That makes no sense unless something is wrong with Uranus's internal heat. Planets generate heat, not from sunlight, though that helps, but from their formation. When a planet forms, gravitational compression heats up the core. That heat radiates outward slowly over billions of years. Jupiter radiates more energy into space than it receives from the sun. Saturn does the same. Neptune does the same. They are all still warm from being born. Uranus is not. Or at least, it is radiating far less heat than it should be. The planet is cold inside and out, and nobody knows why. Either its core cooled off much faster than it should have, or the interior is structured in a way that traps heat and prevents it from reaching the surface, or something happened early in Uranus's history that shut off the normal heat flow. Whatever the cause, Uranus is an ice giant that is colder than it has any right to be. The term ice giant is misleading. Uranus is not made of ice the way a frozen lake is made of ice. It is made of water, methane and ammonia compressed under enormous pressure into a hot, dense fluid that behaves nothing like the liquids or solids we see on Earth. More than 80% of Uranus's mass is this strange high-pressure fluid, sometimes called an icy mantle, sitting above a small rocky core. The mantle is not frozen, It is not boiling. It exists in a supercritical state where the distinction between liquid and gas breaks down. The temperature in the mantle is probably several thousand degrees. The pressure is millions of times what we experience at sea level on Earth. Under those conditions, water stops behaving like water. Methane stops behaving like methane. They become something else, a dense soup of molecules that flows like a liquid but has the density of a solid. Above that mantle sits a thick atmosphere of hydrogen and helium with traces of methane, ammonia, and water vapor. The atmosphere extends upward for thousands of kilometers before thinning into space. There is no surface, no boundary where gas turns to liquid or liquid turns to solid. Just a gradual increase in density and pressure as you descend. If you tried to fly a probe into Uranus, the way the Galileo probe descended into Jupiter, you would pass through increasingly thick layers of gas until the gas was so dense it might as well be liquid. Eventually the pressure would crush your probe flat, but you would never hit a surface. Just deeper and deeper layers of compressed fluid all the way down to the core. From the outside, Uranus looks featureless. The Voyager 2 spacecraft flew past Uranus in January 1986, the only spacecraft ever to visit the planet up close. Voyager came within 50,640 miles of Uranus's cloud tops, close enough to take detailed images and measurements. The images showed a bland blue-green ball with almost no visible cloud features, no storms, no bands like Jupiter, no great red spot. Just a smooth, nearly uniform disk of pale blue. For a long time, scientists assumed Uranus was boring, a quiet planet with a calm atmosphere and nothing much happening. That assumption was wrong. The problem was timing. Voyager arrived during Uranus's northern summer, when the North Pole was pointed almost directly at the Sun. The equator was in twilight. The southern hemisphere was in darkness. The entire planet was in a weird seasonal configuration that does not have an equivalent on Earth. The atmosphere was unusually calm because the temperature gradient between the sunlit pole and the dark hemisphere was not steep enough to drive strong convection. Voyager saw Uranus at its most boring moment, and everyone assumed that was the planet's normal state. Decades later, as Uranus moved along its orbit and the seasons shifted, astronomers using the Hubble Space Telescope and ground-based observatories started seeing more activity. Storms, bright clouds, wind patterns. The planet was waking up. Spring and fall on Uranus, when the equator faces the Sun and both hemispheres receive more balanced sunlight, are far more active than the polar summers. The temperature differences drive convection. Clouds form, winds pick up. The bland blue ball turns into a slightly less bland blue ball with visible weather. The winds on Uranus are fast. Measurements from Voyager and later observations clocked wind speeds up to 560 miles per hour. Those winds blow in the same direction the planet rotates at the equator, but in the opposite direction near the poles. That is strange. On most planets, the winds at the equator blow in the direction of rotation because the equator is moving faster than the poles and the atmosphere gets dragged along. On Uranus, the equatorial winds blow backward, retrograde, opposite the planet's spin. Nobody has a good explanation for why. The most likely answer involves the tilt. The extreme axial tilt creates unusual circulation patterns that do not match any other planet, and the models are still trying to catch up. Uranus rotates retrograde, meaning it spins in the opposite direction of most planets in the solar system. Earth spins west to east. The Sun rises in the east and sets in the west. Uranus spins east to west. If you could stand on Uranus and survive, the Sun would rise in the west and set in the east. Except for half the orbit, the Sun would not rise or set at all. It would just circle the pole. The whole system is backwards and sideways at the same time, like someone assembled the planet from a kit and ignored the instructions. The tilt is the mystery everyone wants to solve. A planet does not just tip over on its own. Something had to knock it sideways. The leading theory is a giant impact. Early in the solar system's history, when planets were still forming and the inner system was full of leftover debris, a massive object, probably about the size of Earth, slammed into Uranus at just the right angle to flip it over. Not a head-on collision, which would have shattered both objects. A glancing blow, the kind of impact that transfers angular momentum without destroying the planet. The collision would have been catastrophic. The impactor would have melted. Uranus's outer layers would have been vaporized. The debris would have scattered into space, possibly forming some of the planet's moons and rings, but the planet itself survived, and when it reformed, it was spinning on its side. This is not a wild guess. We have precedent. Earth's moon is thought to have formed from a similar impact between the early Earth and a Mars-sized object called Theia. That collision ejected material into orbit around Earth, and the material eventually coalesced into the moon. The impact also gave Earth its axial tilt, though Earth only ended up tilted 23 degrees, not 98. Uranus's impact must have been more extreme. Either the impactor was larger, or the angle was more direct, or the energy transfer was more efficient. Whatever the specifics, something hit Uranus hard enough to tip it almost perpendicular to its orbit, and the planet has been spinning that way ever since. Some researchers have proposed a double impact model. In this version, Uranus was hit not once, but twice in relatively quick succession, perhaps within a few million years. The first impact tilted the planet partially. The second impact finished the job. This model explains why Uranus's moons orbit in the planet's equatorial plane instead of being scattered randomly. If a single giant impact had knocked Uranus over, the debris disk that formed the moons should have been tilted relative to the planet's new equator. But the moons orbit in the equatorial plane, suggesting they formed after the tilt was already established. Two impacts, with the second one happening after the first impact's debris had settled, would give you that configuration. Another idea, published more recently, is the lost moon hypothesis. In this scenario, Uranus once had a large moon, maybe the size of Ganymede or Titan, orbiting in a relatively stable configuration. Over time, gravitational interactions between the moon and the sun caused the moon's orbit to drift. Eventually, the moon entered a resonance with the planet's rotation, a feedback loop where the gravitational tugs happened at regular intervals, reinforcing each other. That resonance dragged Uranus's axis over slowly, tipping the planet more and more until it reached its current 98-degree tilt. Then, once the tilt was extreme enough, the resonance broke. The moon's orbit became unstable. The moon was either ejected from the system entirely or crashed into Uranus. Either way, it disappeared, leaving behind a tilted planet and a mystery. The lost moon hypothesis has some advantages over the giant impact model. It explains the tilt without requiring a massive collision. It explains why Uranus's moons orbit in the equatorial plane. And it explains why the planet's rotation rate is retrograde. If a large moon was dragging the axis over through resonance, it could have reversed the planet's spin in the process. The downside is that we have no direct evidence for this lost moon. If it was ejected, it is long gone, drifting somewhere in interstellar space or orbiting the Sun in some distant unknown orbit. If it crashed into Uranus, any trace of it is buried deep in the planet's interior, mixed into the icy mantle and lost forever. Whichever explanation is correct, the result is the same. Uranus ended up tilted at 98 degrees, spinning retrograde, with an atmosphere that barely generates its own heat and a magnetic field that makes no sense. The magnetic field is worth pausing on because it is one of the strangest things about Uranus. On Earth, the magnetic field is generated by convection currents in the liquid iron outer core. The field is roughly aligned with the planet's rotation axis. The magnetic North Pole is close to the geographic North Pole, give or take a few degrees. On Uranus, the magnetic field is tilted 59 degrees away from the rotation axis. The magnetic poles are nowhere near the geographic poles, and the field does not originate from the core. It originates from the icy mantle, the layer of compressed water, methane and ammonia that sits above the core. That fluid is electrically conductive under the extreme pressures inside Uranus, and convection currents in that layer generate the magnetic field. But because the convection happens in a relatively shallow layer, not deep in the core, the field ends up lopsided and misaligned. The result is a magnetic field that wobbles as the planet rotates. The field strength varies depending on where you are in the orbit. The magnetosphere, the region of space dominated by Uranus's magnetic field, is shaped like a corkscrew. As Uranus spins, the magnetosphere spins with it, twisting and untwisting every 17 hours. If you were flying a spacecraft through Uranus's magnetosphere, the magnetic field would change direction and strength constantly, cycling through a full range of orientations every rotation. Voyager 2's magnetometer recorded this as it flew through the system, and the data looked like nothing scientists had seen before. The magnetic field was there, strong enough to trap charged particles and form radiation belts, but it was chaotic, unstable, misaligned, wrong. That wrongness extends to almost everything about Uranus. The planet is tilted when it should be upright. It is cold when it should be warm. Its magnetic field is offset when it should be aligned. Its winds blow backward when they should blow forward, and its atmosphere is nearly featureless when it should be covered in storms. Uranus is a planet that does not fit the models. Every time scientists think they understand it, new observations reveal another layer of strangeness. Voyager 2 is still the only spacecraft to have visited Uranus up close. The flyby lasted a few hours. The spacecraft took images, measured the magnetic field, analyzed the atmosphere, discovered 10 new moons, and confirmed the existence of faint rings around the planet. Then it flew on toward Neptune, leaving Uranus behind. Everything we have learnt about Uranus since 1986 has come from telescopes on Earth or in orbit around Earth. Hubble, ground-based observatories with adaptive optics. The James Webb Space Telescope has not turned its mirror toward Uranus yet, but when it does, it will see the planet in infrared wavelengths that reveal temperature differences and atmospheric composition in ways visible light cannot. Maybe that will answer some of the open questions. Maybe it will just raise new ones. There have been proposals to send another mission to Uranus, a dedicated orbiter, not a flyby. Something that could spend years studying the planet, watching the seasons change, mapping the magnetic field in detail, analyzing the atmospheric chemistry, imaging the moons and rings at high resolution. NASA's Planetary Science Decadal Survey for 2023 to 2032 ranked a Uranus orbiter as the highest priority flagship mission for the next decade. If the mission gets funded and launched, it would not arrive until the 2040s. Uranus is far away. The trip takes over a decade, even with a gravity assist from Jupiter. By the time a spacecraft reaches Uranus, the planet will have moved a quarter of the way through its orbit. The seasons will have shifted. The atmospheric activity will look completely different from what Voyager saw. Standing on Uranus, If you could somehow invent a platform that floated in the atmosphere at the altitude where the pressure matched Earth's sea level, you would see a pale blue sky above you, fading to darker blue or black as you looked towards space. The sun would be a bright star, small and distant. The horizon would curve sharply because Uranus is large, 4 times wider than Earth. Below you, the atmosphere would thicken into haze, methane clouds drifting past at hundreds of miles per hour. Above you, thinner layers of hydrogen and helium, cold and nearly transparent. The temperature would hover around -200 degrees. You would need a heavily insulated suit with active heating, the same kind of equipment you would need on Titan, but colder, much colder. The light would be strange. During the polar summer, the sun would circle the horizon endlessly, never setting, casting a dim, continuous twilight. During the polar winter, the only light would come from stars. No sun, no reflected sunlight from moons unless one happened to be in the sky, just darkness and cold and wind. The equator would get a more normal day-night cycle, but even then, the sun would be so far away that noon would feel like dawn, perpetual twilight, permanent dusk, a world lit by a star that barely registers as a sun. You would not see the surface because there is no surface. Look down and you would see clouds. Look farther down and you would see thicker clouds. Keep looking, and eventually the clouds would blur into a dense haze where visibility drops to 0. Beneath that, the atmosphere would compress into the supercritical icy mantle, and you would lose all sense of where gas ends and liquid begins. It would just be pressure. Increasing, crushing, unrelenting pressure, all the way down to a core you could never reach. Uranus is not trying to kill you the way Venus is. It is not crushing you the way Jupiter is. It is just alien, fundamentally, irreducibly alien. A planet that spins the wrong way, tilted the wrong direction, wrapped in an atmosphere that barely moves and a magnetic field that refuses to align. It is the planet that broke every rule and kept going anyway, spinning on its side in the outer dark, too cold to care and too far away to notice. And yet, for all its strangeness, Uranus is not the strangest ice giant. That title belongs to Neptune, the planet beyond Uranus, the planet at the edge of the classical solar system, the one with winds so fast they should not exist and storms that appear and disappear without warning. Neptune is farther, colder, darker, and somehow it is more active than Uranus, more violent, more hostile. The next step into the abyss is waiting, and it does not make sense until you see it. Neptune should not have weather. Not like this. Not at this distance. Not with this little energy to work with. The planet sits 30 times farther from the sun than Earth does. At that distance, sunlight is 900 times weaker than what we receive. The sun from Neptune's cloud tops looks like a very bright star, nothing more. A pinpoint of light in a black sky that provides almost no heat, almost no energy, barely enough radiation to register on an instrument. By every reasonable model of planetary atmospheres, Neptune should be a frozen ball of gas with sluggish winds and almost no weather. A cold, dead world circling the outer edge of the solar system in silence. Instead, Neptune has the fastest winds ever measured on any planet in the solar system. Winds that blow at 1,300 miles per hour. Winds that exceed the speed of sound on Earth by a factor of 1.5. Winds so fast that they rip storms apart before the storms can fully form, that carve jet streams through the atmosphere like invisible blades cutting through fog. Winds that have no right to exist because there is no obvious source of energy powerful enough to drive them. That is the central mystery of Neptune. The planet is doing something it should not be able to do, and after more than 3 decades of studying it, planetary scientists are still not entirely sure how it works. Neptune is the 8th and final major planet in the solar system. It is slightly smaller than Uranus, about 30,000 miles across, but it is more massive, more dense, more tightly packed. Like Uranus, it is an ice giant, meaning most of its mass is not hydrogen and helium like the gas giants Jupiter and Saturn, but water, methane and ammonia compressed into a hot, dense fluid under millions of atmospheres of pressure. Above that fluid mantle sits a thick atmosphere of hydrogen and helium with traces of methane. The methane absorbs red light and reflects blue, giving Neptune its distinctive deep blue color. From a distance, Neptune looks like a sapphire, a rich, vibrant blue that stands out against the black of space. It is one of the most beautiful planets in the solar system. It is also one of the most violent. The temperature at Neptune's cloud tops averages around 55 Kelvin, that is -218 degrees Celsius, -361 Fahrenheit, cold enough that methane freezes into ice crystals and drifts through the upper atmosphere like snow. Cold enough that the hydrogen and helium surrounding those methane clouds are only a few dozen degrees above absolute zero, the coldest possible temperature in the universe. Neptune is one of the coldest places in the solar system. Only the outer reaches of the Kuiper belt and the distant comets in the Oort cloud are colder. And yet Neptune is warm, not on the surface, inside. Deep inside, the planet is generating heat, a lot of heat. Neptune radiates 2.6 times more energy into space than it receives from the Sun. For every watt of sunlight that hits the planet, Neptune puts out 2.6 watts of its own internally generated energy. That ratio is higher than any other planet in the solar system. Jupiter radiates about 1.6 times the energy it receives. Saturn about 1.8. Uranus, for reasons nobody fully understands, barely radiates any excess heat at all. Neptune is the overachiever, the planet that refuses to cool down. That internal heat is what powers the winds. On Earth, weather is driven by temperature differences. Warm air at the equator rises, cool air at the poles sinks, and the temperature gradient between them drives wind and storms. The energy comes from the sun. Without sunlight, Earth's weather would stop. The atmosphere would freeze and fall to the ground as snow within weeks. Neptune gets almost no energy from the sun, so the temperature gradient caused by solar heating is tiny. But the planet is generating its own heat from the inside, and that heat is being released unevenly across the surface. Some regions of the atmosphere sit above hotspots where more internal heat is escaping. Other regions sit above cooler areas. The result is a temperature gradient, not caused by the sun, but caused by the planet's own internal engine. And that gradient is enough to drive winds that dwarf anything on Earth. The winds on Neptune blow in bands, similar to Jupiter and Saturn, but faster, much faster. The fastest winds measured by Voyager 2, the only spacecraft ever to visit Neptune, clocked in at around 1,200 miles per hour near the equator. More recent observations using the Hubble Space Telescope and ground-based observatories have pushed that number even higher, closer to 1,300 miles per hour. Those are peak speeds, measured in narrow jet streams where the wind is most concentrated. Average wind speeds across the planet are lower, a few hundred miles per hour, but even that is extreme. For comparison, the fastest winds ever recorded on Earth, inside tornadoes and tropical cyclones, top out around 300 miles per hour. Neptune's average winds are faster than Earth's most violent storms. Here is what makes this even stranger. The winds blow in thin layers. Voyager 2's instruments and later modeling work showed that the extreme wind speeds are confined to the upper few hundred miles of Neptune's atmosphere. Below that, the winds die down. The deep atmosphere is relatively calm. The energy that drives the winds is concentrated in a shallow surface layer where internal heat meets the cold of space, creating a narrow zone of intense convection. Think of it like a pot of water on a stove. The heat comes from below. The surface of the water is where the temperature difference is steepest, where hot water meets cold air, and that is where you see the most turbulence. Neptune's atmosphere works the same way. The turbulence is concentrated at the boundary, but here is the problem. Even with internal heat, Neptune should not have winds this fast. The amount of energy required to sustain 1,300 mile-per-hour winds is enormous, and the math does not quite add up. The internal heat Neptune is generating should be enough to drive some weather, yes, but not weather this violent. Something else is going on. Either the heat is being released more efficiently than the models predict, or there is some kind of feedback loop in the atmosphere that amplifies the wind speeds beyond what the raw energy input would suggest, or both. Planetary scientists are still working on it. The wind patterns themselves are strange. On Jupiter and Saturn, the winds blow in alternating bands. Eastward winds at some latitudes, westward winds at others, creating a striped pattern of jet streams that wraps around the planet. Neptune has similar bands, but the directions are reversed in ways that do not match the gas giants. The equatorial winds blow westward, retrograde, opposite the planet's rotation. That is unusual. On most planets, the equator rotates faster than the poles, and the atmosphere gets dragged along, creating eastward winds. On Neptune, the winds fight against the rotation. Nobody is entirely sure why. The most likely explanation involves the planet's internal heat distribution and the way convection cells in the atmosphere interact with the planet's rotation, but the models are still rough. Neptune also has storms. Big ones, transient ones, storms that appear, rage for a few years, and then vanish without explanation. The most famous one was discovered by Voyager 2 in August 1989, when the spacecraft flew past Neptune on its way out of the solar system. Voyager spotted a massive dark oval in Neptune's southern hemisphere, roughly the size of Earth. The storm was a high-pressure anticyclone, similar in structure to Jupiter's Great Red Spot, but darker, much darker. Instead of being red or orange, it was a deep blue-black, a hole in the atmosphere where the clouds were thinner and you could see deeper into the planet. Scientists called it the Great Dark Spot. The Great Dark Spot rotated counterclockwise, spinning once every 16 days. The winds around its edge blew at over 700 miles per hour. White methane clouds clung to the edges of the storm, bright streaks against the dark interior, constantly forming and dissipating as the storm churned. Voyager watched the storm for several months as the spacecraft approached, flew past, and then receded into the distance. The images showed a dynamic, turbulent system, constantly changing shape, pulsing and warping as it spun. Then Voyager left, and for several years nobody could see Neptune well enough to track the storm in detail. In 1994, the Hubble Space Telescope turned its newly repaired optics toward Neptune. Astronomers expected to see the Great Dark Spot still spinning in the southern hemisphere. It was gone, completely gone. No trace of it left in the atmosphere. In its place, a new dark spot had appeared in the northern hemisphere, smaller than the original, but similar in structure. Scientists called it the Northern Great Dark Spot. By the late 1990s, that storm had also disappeared. In 2000, Hubble spotted another dark spot forming in the southern hemisphere. It lasted a few years, then faded. In 2018, another one appeared. Still there as of the last observations, but who knows for how long. Neptune's storms do not last. They are not like Jupiter's great red spot, a feature that has persisted for over a century. Neptune's dark spots form, rage for a few years, and then dissipate. Nobody knows why they form in the first place or what causes them to collapse. The leading theory is that they are vortices driven by convection from below, but the details are murky. The storms seem to be tied to the release of internal heat, but the mechanism that creates them and the mechanism that destroys them are both poorly understood. What is clear is that Neptune's atmosphere is dynamic in ways that surprised everyone. The planet looked calm in Voyager's images, a smooth blue sphere with a few dark spots and some bright clouds. But the reality is that the atmosphere is constantly churning, constantly rearranging itself, constantly generating and destroying weather systems on timescales of years. Then there is the diamond rain. This is not confirmed. It is not directly observed. It is a hypothesis based on lab experiments and theoretical models, but it is one of the most compelling ideas to come out of planetary science in the last 2 decades. The idea is that deep inside Neptune, in the region where the atmosphere transitions into the fluid mantle, the pressure and temperature are high enough to break apart methane molecules. Methane is made of carbon and hydrogen. Under extreme pressure, the carbon atoms can separate from the hydrogen and clump together. Under even more extreme pressure, those clumps of carbon can crystallize into diamond. The conditions inside Neptune are right on the edge of where this could happen. The pressure about 5,000 miles below the cloud tops is estimated to be around 6 million atmospheres. The temperature is around 5,000 degrees Fahrenheit. Laboratory experiments have shown that at those pressures and temperatures, carbon extracted from hydrocarbons like methane can form diamond crystals, not large diamonds, tiny ones. Microscopic at first, then growing larger as they sink deeper into the planet. The diamonds would be denser than the surrounding fluid, so they would fall, raining down through the mantle like hailstones, sinking toward the core over the course of thousands or millions of years. If this is happening, and the math suggests it could be, then Neptune's interior is filled with diamonds, not a few scattered crystals, a constant rain of diamonds falling through a sea of compressed water and methane, accumulating in a layer around the core. Some estimates suggest there could be millions of tons of diamond inside Neptune, maybe more. Enough that if you could somehow mine it, you would flood the Earth market and make diamonds worthless overnight. The same process would happen on Uranus. Same internal pressure, same temperature, same chemistry. Both ice giants might be raining diamonds right now, and we would have no way to detect it from the outside. The diamonds are too deep. They are buried under thousands of miles of dense fluid and thick atmosphere. No probe we could build would survive the descent. The pressure would crush it long before it got close. The heat would melt the electronics. We cannot go there. We can only model it and run lab experiments that simulate the conditions and show that yes, under the right circumstances, methane breaks apart and carbon crystallizes and you get diamond rain. It is one of those ideas that sounds like science fiction but is probably real. Neptune is not just a cold blue planet with fast winds. It is a factory. A place where the laws of chemistry under extreme pressure create materials that do not form naturally anywhere on Earth. And it is doing this continuously, quietly, in the deep interior where no instrument will ever reach. The internal heat that powers all of this, the winds and the storms, and possibly the diamond rain, comes from leftover energy from Neptune's formation. When the planet formed 4.5 billion years ago, gravitational collapse heated up the interior. That heat has been radiating outward ever since, slowly leaking into space. Most planets have cooled off significantly over the last few billion years. Neptune has not. Either it started out hotter than expected, or it is cooling more slowly than the models predict, or there is some other heat source we have not accounted for. One possibility is that the process of separating heavy elements from lighter ones in the interior, the same process that might create diamond rain, releases additional energy. As diamonds and other dense materials sink toward the core, they release gravitational potential energy, and that energy heats the surrounding fluid. It is a feedback loop. The heat drives convection. Convection drives differentiation. Differentiation releases more heat. The cycle keeps going, sustaining itself over billions of years. Neptune rotates quickly. One day on Neptune is about 16 hours and 6 minutes. That is slightly longer than Jupiter's 10-hour day, but much shorter than Earth's 24-hour day. The fast rotation creates strong Coriolis forces, which help organize the winds into the banded jet stream patterns. The planet's magnetic field, like Uranus's, is tilted relative to the rotation axis and offset from the center. The magnetic field is tilted about 47 degrees, and it originates from the icy mantle, not the core. This creates a lopsided magnetosphere that wobbles as the planet rotates, just like Uranus. The field is strong enough to trap charged particles from the solar wind, creating radiation belts, but the belts are weaker than Jupiter's, still dangerous, still enough to fry unshielded electronics, but manageable if you design your spacecraft properly. Voyager 2 is the only spacecraft that has visited Neptune up close. The flyby happened on August 25, 1989. Voyager came within 3,000 miles of Neptune's cloud tops, closer than it got to any other planet during its grand tour of the outer solar system. The spacecraft took thousands of images, measured the magnetic field, analyzed the atmospheric composition, discovered 6 new moons, and confirmed the existence of faint rings around the planet. The rings are made of dark material, possibly organic compounds mixed with ice, and they are so thin and faint that they were almost invisible until Voyager flew past and imaged them with its cameras pointing back toward the sun, using backlighting to make the particles stand out. Then Voyager flew on. Its trajectory after Neptune sent it out of the plane of the solar system, heading south, away from the sun, into interstellar space. It is still out there, billions of miles away, coasting through the dark. The data it sent back in 1989 is still the best data we have on Neptune's atmosphere and interior. Everything else comes from telescopes, Hubble, ground-based observatories. The James Webb Space Telescope will eventually turn its infrared instruments toward Neptune and see the planet in wavelengths that reveal heat distribution and atmospheric chemistry. That data will help, but it will not replace a dedicated mission. There have been proposals for a Neptune orbiter, a spacecraft that would spend years studying the planet, watching the seasons change, tracking the storms, measuring the wind speeds over time, imaging the moons and rings at high resolution. Neptune's year is 165 Earth years. One season lasts over 40 years. Voyager saw Neptune during southern summer. The northern hemisphere was in darkness. The planet has moved about a fifth of the way through its orbit since then. The seasons have shifted. The atmospheric activity looks different now than it did in 1989. A dedicated orbiter could watch those changes unfold, could measure how the wind patterns shift as the solar heating changes, could track the formation and dissipation of dark spots in real time. The mission has not been funded. Neptune is far. The trip takes over a decade, even with a gravity assist from Jupiter. A mission launched today would not arrive until the late 2030s at the earliest. By that time, the planet will have moved another eighth of the way through its orbit. The southern hemisphere will be heading into fall. The storms might look completely different, or they might look the same. We do not know because we have only seen Neptune in detail for a few months, and that was over 3 decades ago. Neptune has 14 known moons. Most of them are small, irregular, probably captured asteroids or Kuiper belt objects that wandered too close and got pulled into orbit. One of them is large, enormous actually. Triton, Neptune's largest moon, is the 7th largest moon in the entire solar system. It is bigger than Pluto, bigger than Eris, bigger than every other Kuiper belt object we have discovered, and it is orbiting Neptune backward. Triton orbits retrograde, meaning it moves in the opposite direction of Neptune's rotation. That is almost unheard of for a large moon. Small, irregular moons can have retrograde orbits because they were captured and their original trajectories got frozen in place. But large moons are supposed to form from the same disk of material that formed the planet, and everything in that disk rotates in the same direction. Triton did not form with Neptune. It formed somewhere else, probably in the Kuiper belt, and then got captured by Neptune's gravity at some point in the distant past. The capture process would have been violent. Triton's original orbit would have been highly elliptical, swinging close to Neptune and then far out into space. Tidal forces from Neptune would have circularized that orbit over millions of years, pulling Triton into the nearly circular path it follows today. But the orbit is still retrograde. Triton is still moving the wrong way. That retrograde motion means Triton is doomed. Tidal forces are still acting on the moon, and they are slowly pulling it closer to Neptune. Eventually, maybe in a few 100 million years, maybe a billion, Triton will cross Neptune's Roche limit, the distance at which tidal forces overcome the moon's own gravity and tear it apart. When that happens, Triton will shred into a ring of debris around Neptune, a ring far more massive and spectacular than the faint rings the planet has now. But that is a long time from now. For now, Triton is intact, orbiting backward 6 days to complete one orbit, tidally locked, so the same face always points toward Neptune. Triton is geologically active. Voyager 2 discovered geysers erupting from Triton's surface during its flyby in 1989. Not water geysers, nitrogen geysers. The surface temperature on Triton is 38 Kelvin, cold enough that nitrogen freezes solid. But beneath the surface, possibly heated by tidal flexing or radioactive decay, pockets of liquid nitrogen exist under pressure. When that pressure builds up enough, it breaks through the surface and erupts, shooting nitrogen gas and dark organic particles miles into the thin atmosphere. The plumes drift downwind and settle back onto the surface, creating dark streaks across the icy plains. Triton is one of the few geologically active moons in the outer solar system, and the only one known to have active nitrogen geysers. The surface of Triton is bizarre, smooth plains of frozen nitrogen dotted with impact craters, cantaloupe terrain, a region where the surface is broken into ridges and valleys that look like the skin of a cantaloupe melon. Calderas, the collapsed remnants of old cryovolcanoes where water or ammonia erupted instead of lava. Triton is a moon that has been resurfaced multiple times over its history, wiped clean by cryovolcanism and nitrogen frost and whatever else happens when you take a Kuiper belt object and drag it into a close orbit around an ice giant. The result is a moon that looks nothing like anything else in the solar system. a frozen patchwork of terrains that should not exist together, stitched across a surface that is still changing. Standing on Triton, if you could survive the cold and the vacuum, you would see Neptune filling half the sky. The planet would hang there, enormous, deep blue, banded with faint clouds, rotating slowly as Triton orbited around it. You would see the dark spots, if they were present, drifting across the face of the planet like bruises. The sun would be a bright star, far away, barely warm. The ground beneath you would be nitrogen ice, hard as concrete, smooth in some places, ridged and broken in others. The horizon would be close because Triton is small, only about 1,600 miles across. The sky would be black except for Neptune and the sun and the distant stars. No sound, no wind, just silence and cold and the slow march of Triton across its doomed orbit. Neptune is the edge, the last of the major planets. Beyond Neptune, there is no planet. Just the Kuiper Belt, a scattering of icy bodies too small and too far apart to hold your attention. Just comets and dwarf planets and debris, frozen relics from the solar system's formation, drifting in the outer dark. Neptune marks the boundary. Inside Neptune's orbit, you have planets, gas giants and ice giants and rocky worlds, all distinct, all violent, all terrifying in their own ways. Outside Neptune's orbit, you have the edge, the place where the sun's influence fades and the solar system starts to blur into interstellar space. But the edge is not safe. The Kuiper Belt is not empty, and the objects out there, the ones we are just starting to catalogue, have their own horrors. Worlds so cold that the atmosphere freezes and falls to the ground. Worlds with orbits so elliptical they spend centuries in darkness before swinging back toward the sun for a few brief years of dim light. Worlds we did not know existed until a few decades ago, and we still do not know what they look like up close. The solar system does not end at Neptune. It just stops pretending to make sense. Beyond the ice giants, the rules change again. The familiar planets with their moons and their storms give way to something stranger, something older. The debris field at the edge of creation, where the solar system trails off into nothing and the void begins. That is where we are going next, past the planets, into the belt of forgotten worlds. The Kuiper Belt and beyond, where the solar system finally runs out of momentum and the sun becomes just another star. Beyond Neptune, the solar system does not end. It stops pretending to be organized. The planets are done. The familiar hierarchy of rocky worlds and gas giants gives way to a scattered field of debris, icy bodies frozen in orbits so distant that the sun shrinks to a point of light barely brighter than the stars around it. This is the Kuiper Belt, a disk of leftover material from the solar system's formation, stretching from Neptune's orbit at 30 astronomical units out to at least 50, possibly farther. 1 astronomical unit is the distance from the Earth to the Sun. 50 astronomical units is 3 billion miles past Neptune. At that distance, sunlight is so weak that standing on one of these frozen worlds at high noon would feel like standing on Earth under a full moon. Dim, colorless, cold enough that your breath would freeze mid-exhale and shatter on the ground. The Kuiper Belt is not empty. There are thousands of objects out here, tens of thousands, maybe more. Most of them are small, a few miles across, chunks of ice and rock tumbling through the void. Some are larger, much larger. Large enough to have their own gravity, their own moons, their own tenuous atmospheres that freeze out of the sky and collapse onto the surface when the orbit carries them too far from the sun. We call these objects dwarf planets, a classification invented in 2006 to deal with the fact that the outer solar system is messier than anyone expected. Pluto used to be the 9th planet. For 76 years, from its discovery in 1930 to its demotion in 2006, Pluto sat at the edge of the solar system as the smallest, coldest, strangest planet we knew about. Then astronomers started finding more objects like it. Objects in the Kuiper belt with similar sizes, similar orbits, similar compositions. Eris, discovered in 2005, turned out to be slightly more massive than Pluto. Makemake, Haumea, Quaoar, Sedna, a growing list of icy worlds that did not fit neatly into the category of planet but were too large to ignore. The International Astronomical Union redefined what a planet is, and Pluto got bumped down to dwarf planet. The decision was controversial. Some astronomers still argue about it, but the reclassification did not change what Pluto is. It just changed what we call it. Pluto is still there, orbiting the Sun every 248 years, locked in a slow dance with the largest of its 5 moons. And it is still one of the strangest, most hostile places in the solar system. Pluto is small, 1,473 miles across, about 2/3 the diameter of Earth's moon. Small enough that if you placed it on a map of the United States, it would stretch from roughly the east coast to the Midwest, not quite reaching the Rockies. For comparison, our moon is 2,100 miles across. Mercury, the smallest planet, is 3,000 miles across. Pluto is not just small for a planet, it is small for a moon. Tron, Pluto's largest moon, is 750 miles across, more than half Pluto's diameter. The two orbit each other so closely that the center of mass between them sits in the empty space between the two bodies, not inside Pluto. That makes Pluto and Charon a binary system, two objects orbiting a shared point in space, rather than a planet and a moon in the traditional sense. The distance from the Sun averages 3.6 billion miles. That is 39.5 times farther than Earth. Pluto's orbit is not circular. It is elliptical, stretched out, so that at its closest approach to the Sun, called perihelion, Pluto dips inside Neptune's orbit, coming within 30 astronomical units. At its farthest point, aphelion, Pluto swings out to nearly 50 astronomical units. The orbit is also tilted 17 degrees relative to the plane where the planets orbit. Pluto does not follow the rules. It never has. The surface temperature averages -387 degrees Fahrenheit, -232 Celsius, 41 Kelvin. That is cold enough that nitrogen, which makes up 78% of Earth's atmosphere, freezes solid. On Pluto, nitrogen is not a gas you breathe, it is ice. It forms glaciers, plains, frost deposits that cover vast stretches of the surface. Methane, which is a gas on Earth and a liquid on Titan, is also frozen solid on Pluto. So is carbon monoxide. Water, the substance we think of as liquid, is harder than steel at those temperatures. On Pluto, water ice is bedrock. Mountains are made of it. The crust is made of it. It is as permanent and unyielding as granite on Earth. But Pluto does have an atmosphere, a thin one, extremely thin. The surface pressure is about 1 microbar, 100,000th of Earth's atmospheric pressure. That is barely above a vacuum. Stand on Pluto without a pressure suit, and the lack of pressure would not kill you immediately the way it would on Mars. You would still die, obviously, from the cold and the lack of oxygen, but the pressure itself is so low it might as well be zero. The atmosphere is mostly nitrogen, with traces of methane and carbon monoxide. It extends upward for hundreds of miles, far higher than Earth's atmosphere. Because Pluto's gravity is so weak, that gas molecules can drift farther before falling back. The atmosphere was discovered in 1988, not by a spacecraft, but by watching Pluto pass in front of a distant star. Astronomers call this a stellar occultation. As Pluto moved across the starlight dimmed gradually rather than blinking out instantly. That gradual dimming meant there was something around Pluto bending the light, something with enough substance to affect the star's brightness. An atmosphere, not a thick one, not a stable one, but an atmosphere nonetheless. The New Horizons spacecraft, the only mission ever sent to Pluto, confirmed this during its flyby in July 2015. The probe flew within 7,800 miles of Pluto's surface, close enough to measure the atmosphere directly. The data showed that the atmosphere is not static. It is slowly escaping into space, leaking away at a rate of several tons per hour. Pluto's gravity is too weak to hold onto the gas permanently. Nitrogen molecules, heated slightly by the dim sunlight, gain enough energy to reach escape velocity and drift off into the Kuiper belt. Over millions of years, Pluto will lose its atmosphere entirely unless something replenishes it. And something does. The atmosphere is replenished by sublimation. Pluto's orbit is so elliptical that the distance from the Sun changes dramatically over the course of its 248-year trip. When Pluto is near perihelion, closer to the Sun, the surface warms up slightly, not much, maybe a few degrees. But that is enough to turn some of the nitrogen ice directly into gas without melting it first. Sublimation. The gas rises, thickens the atmosphere, increases the surface pressure. When Pluto swings back out toward aphelion, farther from the Sun, the surface cools. The nitrogen gas freezes and falls back to the ground as snow. The atmosphere collapses, the surface pressure drops. This cycle repeats every orbit. For a few decades, Pluto has an atmosphere. For the next few decades, it does not. The planet breathes in and out over the course of centuries. Right now, Pluto is moving away from the Sun. Perihelion was in 1989. The atmosphere is collapsing. By the time Pluto reaches aphelion in 2013, decades from now, most of the atmosphere will have frozen out and the surface pressure will be even lower than it is today. The nitrogen will lie on the ground in drifts and plains and glaciers, waiting for the orbit to bring Pluto back toward the Sun so it can sublimate again and rebuild the atmosphere. This is not weather in any normal sense. This is a planetary scale phase change happening over human lifetimes. New Horizons showed us what Pluto looks like up close, and the answer surprised everyone. Before the flyby, most models predicted a heavily cratered surface, ancient and dead, unchanged for billions of years. What the probe found was a world that has been resurfaced recently, geologically speaking. The most famous feature, a heart-shaped region informally named Tombor Regio, after Clyde Tombaugh, the astronomer who discovered Pluto in 1930, is a vast plain of nitrogen ice, smooth, nearly flat, almost no craters. That means the surface is young, no more than a few 100 million years old, possibly much younger. Something has erased the craters. Something has repaved that region with fresh ice. The western lobe of the heart, called Sputnik Planitia, is a massive nitrogen glacier covering an area larger than Texas. The ice is not static. It flows slowly, driven by convection. Warmer ice, heated slightly by Pluto's internal heat, rises from below. Cooler ice at the surface sinks. The result is a pattern of polygonal cells, each one about 10 to 20 miles across, where the ice is churning over on timescales of a few 100,000 years. The process is similar to convection in a pot of boiling water, except the water is frozen nitrogen and the heat source is the faint warmth leaking out of Pluto's interior. The glacier is alive, in a sense constantly rearranging itself, erasing any features that form on the surface. Surrounding the plains are mountains, tall mountains. Some of them rise over 2 miles above the surrounding terrain. They are made of water ice, the bedrock of Pluto, pushed upward by forces that are not entirely understood, possibly tectonic, possibly the result of ice expanding as it freezes. Water is one of the few substances that expands when it solidifies, and on Pluto, water ice is the structural material that everything else rests on. If subsurface water froze and expanded, it could push up ridges and peaks the way tectonic forces push up mountains on Earth. Except on Pluto, the water is not liquid in the normal sense. It is ice warmed slightly by internal heat or pressure, soft enough to flow over geologic timescales, hard enough to hold its shape over shorter periods. The surface is not uniform in color. Parts of it are bright white, covered in fresh nitrogen frost. Other parts are dark reddish-brown, stained by organic molecules called tholins. Tholins form when ultraviolet light from the sun breaks apart methane and nitrogen in the atmosphere. The fragments recombine into more complex hydrocarbons, long-chain molecules that do not exist in nature on Earth. These molecules drift down from the atmosphere and settle on the surface, giving Pluto its mottled appearance. The reddish regions are older, places where the tholins have had time to accumulate. The white regions are younger, places where fresh ice has recently covered the surface and buried the organic stains. Charon, Pluto's largest moon, orbits just 12,400 miles away. That is about 1/20th the distance between Earth and our moon. From Pluto's surface, Charon does not rise or set. It hangs in the sky, motionless, locked in the same position day after day, year after year, because Pluto and Charon are tidally locked. Pluto's day is 6.4 Earth days long. Charon's orbit is also 6.4 Earth days. The two rotate and orbit in perfect sync. One face of Pluto always points toward Charon. One face of Charon always points toward Pluto. If you stood on the side of Pluto facing Charon, the moon would be a constant presence in the sky, never moving, never changing position, just hanging there like a grey disk 3.5 times wider than our moon appears from Earth. If you stood on the other side of Pluto, you would never see Charon, ever. The moon would be permanently hidden below the horizon. You could walk around the entire planet and never catch a glimpse of it unless you crossed into the hemisphere that faces Charon. The tidal lock is absolute. Charon's surface is heavily fractured. The New Horizons images showed long canyons and ridges cutting across the moon's surface, some of them hundreds of miles long and several miles deep. The fractures suggest that Charon's interior froze and expanded at some point in its history, cracking the crust like an eggshell. The surface is also divided into two distinct regions. The northern hemisphere is dark, covered in a reddish-brown material that is probably tholins captured from Pluto's atmosphere, or produced locally by radiation breaking apart methane ice. The southern hemisphere is brighter, covered in water ice mixed with ammonia. The boundary between the two regions is sharp, a clear line cutting across the equator. Nobody knows why the two hemispheres are so different. Charon has no atmosphere, no weather, no geological activity that we can detect. It is a frozen, fractured ball of ice orbiting Pluto in silence. Standing on Charon, you would see Pluto filling the sky, blue and brown and white, rotating slowly, completing one rotation every 6.5 days. The sun would be a bright star, far away, providing almost no warmth. The horizon would be close, only about 20 miles away, because Charon is small and its gravity is weak. The ground would be water ice, hard as rock, cracked and ridged, covered in a thin layer of red-brown dust. No sound, no movement, just you and Pluto and the distant stars. The other four moons, Styx, Nix, Kerberos and Hydra, are much smaller. Irregular chunks of ice a few dozen miles across, tumbling through orbits farther out from Pluto and Charon. They are probably captured Kuiper Belt objects, pieces of debris that wandered too close and got pulled into orbit. New Horizons imaged them during the flyby, but the resolution was not high enough to show much detail. They are there, they orbit. That is about all we know. Pluto is not the only dwarf planet in the Kuiper Belt. Eris, discovered in 2005, sits even farther out, currently about 96 astronomical units from the Sun. Eris is slightly smaller than Pluto in diameter, but it is more massive, denser. Its surface is covered in methane ice, and spectroscopic observations suggest the ice is bright white, reflecting nearly all the sunlight that hits it. Eris has one known moon, Dysnomia, orbiting at a distance of about 23,000 miles. The surface temperature on Eris is around -396 degrees Fahrenheit, colder than Pluto because it is farther from the Sun. Eris's orbit is even more elliptical than Pluto's, taking 560 years to complete. At its closest, Eris comes within 38 astronomical units of the Sun, closer than Pluto at aphelion. At its farthest, it swings out to 98 astronomical units. Most of the time, Eris is in the outer dark, so far from the Sun that even calling it part of the solar system feels generous. Makemake, another Kuiper Belt dwarf planet, is slightly smaller than Pluto, about 870 miles across. It orbits at about 45 astronomical units, taking 310 years to complete one orbit. Makemake's surface is covered in methane and nitrogen ice, similar to Pluto, and it has a very thin atmosphere, detected during a stellar occultation in 2011. The atmosphere is so thin it is barely there, just a faint haze of nitrogen and methane clinging to the surface. Makemake has one known moon, discovered in 2016, orbiting at a distance of about 13,000 miles. The moon is dark, much darker than Makemake itself, suggesting it is made of different material, possibly organic rich compounds or carbon. There are others. Haumea, an elongated dwarf planet that spins so fast it has stretched into an ellipsoid shape, rotating once every 4 hours. Haumea has 2 moons and a ring system, the only dwarf planet known to have rings. Quaoar, orbiting at about 43 astronomical units, with a surface covered in water ice and possibly a subsurface ocean kept liquid by tidal heating. Sedna, an object so far out that its perihelion is 76 astronomical units and its aphelion is nearly 1,000 astronomical units. Sedna takes 11,000 years to complete one orbit. 11,000 years, that is longer than recorded human history. Sedna is so distant that some astronomers think it belongs to a different category entirely, not part of the Kuiper Belt, but part of the inner Oort cloud, the region where comets are born. These objects are difficult to study because they are so far away and so faint. Even the largest ones, Pluto and Eris, are barely visible in ground-based telescopes. Getting detailed images requires space telescopes like Hubble or the James Webb Space Telescope, and even then, the resolution is not great. Pluto, before New Horizons, was a blurry blob in Hubble's images. We could see that it had light and dark regions, but we could not make out mountains or plains or glaciers. We had no idea what the surface looked like. New Horizons changed that, but only for Pluto and Charon. Every other dwarf planet in the Kuiper Belt is still a mystery. We know they are there. We know roughly how big they are and what their surfaces are made of, but we have never seen them up close. There are no missions planned to visit Eris or Makemake or any of the other Kuiper Belt objects. The distances are too great, the travel times are too long. New Horizons took 9.5 years to reach Pluto, and that was with a gravity assist from Jupiter that accelerated the spacecraft to over 36,000 miles per hour, making it the fastest object ever launched from Earth. A mission to Eris would take even longer because Eris is farther out and there is no convenient gravity assist available. You would be looking at 15 to 20 years of flight time, maybe more, just to reach an object that might not have much to show you. The funding does not exist. The scientific community has other priorities. Pluto was a once-in-a-generation mission, and it worked because Pluto has name recognition. People know Pluto. They do not know Makemake. The Kuiper Belt itself is a relic, a fossil record of the solar system's formation, preserved in ice and scattered across billions of miles of empty space. When the solar system formed 4.5 billion years ago, a disk of gas and dust surrounded the young sun. The inner part of the disk was hot, so only metals and rocks could condense. Those materials formed the rocky planets. The outer part of the disk was cold, so water, methane, and ammonia could freeze. Those ices, mixed with rock, formed the cores of the gas giants and ice giants. Farther out still, beyond Neptune's orbit, the material was too spread out to form a planet. The ices clumped together into millions of small bodies, each one a few miles to a few hundred miles across. Those bodies are the Kuiper Belt. They are leftovers, pieces that never got incorporated into anything larger. And they have been sitting out there, largely unchanged, for the entire history of the solar system. Studying the Kuiper Belt tells us what the solar system looked like when it was young. The chemical composition of these objects reflects the composition of the original disk. The isotopic ratios, the relative abundances of different elements, the organic molecules found on their surfaces, all of that is data about the conditions that existed 4.5 billion years ago. Pluto's surface, covered in nitrogen ice and organic tholins, is a snapshot of the early solar system. The methane on Makemake, the water ice on Quaoar, the strange elongated shape of Haumea, every feature is a clue, a piece of evidence about how planets form and what materials were available and how those materials got distributed. The danger of exploring these worlds is not the same kind of danger you face on Venus or Jupiter. Nobody is going to get crushed by atmospheric pressure or fried by radiation belts in the Kuiper Belt. The danger is distance, cold, darkness. The sun is so far away that solar panels barely work. Spacecraft need nuclear power sources, radioisotope thermoelectric generators that convert the heat from decaying plutonium into electricity. Communication is slow. A radio signal from Pluto takes 4.5 hours to reach Earth. 4.5 hours. Send a command to a spacecraft at Pluto and you will not get a response for 9 hours. That makes real-time control impossible. Everything has to be pre-programmed. Every maneuver, every observation, every adjustment has to be planned months in advance and uploaded to the spacecraft before it gets there. If something goes wrong, you find out hours after it has already happened, and there is nothing you can do about it. The cold is another problem. Keeping instruments warm enough to function at -400 degrees Fahrenheit requires constant heating. Batteries drain faster. Electronics fail more easily. Materials that work fine at room temperature become brittle and crack at Kuiper Belt temperatures. Every component on a spacecraft sent to these regions has to be tested and rated for extreme cold. The Voyager probes, which are now in interstellar space, are still sending back data, but only because their radioisotope generators are still producing heat. Once those generators run out of fuel, the spacecraft will freeze and go silent. The darkness is disorienting. On Earth, even at night, there is scattered light from the moon, from stars, from the atmosphere itself. In the Kuiper belt, there is no scattered light. The sky is black. The sun is a point. The only illumination comes from starlight, and starlight is not enough to see by. Any surface you stand on would be lit by the equivalent of a very dim flashlight held at arm's length. You could see the broad shapes of the landscape. You could make out the horizon, but details would be invisible. Everything would blend together into shades of grey and black. And yet, these worlds are not dead, not entirely. Pluto has an atmosphere that freezes and thaws. It has glaciers that flow. It has mountains that formed recently, geologically speaking, pushed up by forces we do not fully understand. Charon has fractures that suggest a violent past, a time when the moon's interior expanded and cracked the surface. Eris and Makemake have methane ice on their surfaces, ice that sublimates and reforms over the course of their long orbits. These are not inert rocks. They are dynamic, evolving, responding to the faint energy they receive from the sun and the heat still leaking out of their interiors. The Kuiper belt is the edge of the familiar solar system. Beyond it lies the scattered disk, a region where the orbits become even more elliptical and tilted, where objects like Sedna and Gong and Leilakahonoa drift in long, slow loops that take them thousands of astronomical units from the sun. Beyond that is the Oort cloud, a spherical shell of comets surrounding the entire solar system, extending out to 100,000 astronomical units or more. The Oort cloud is so distant that we have never directly observed it. We know it exists because comets come from somewhere, and their orbits trace back to that region. But no spacecraft will reach the Oort cloud in our lifetimes. Voyager 1, the most distant human-made object, is currently about 160 astronomical units from the Sun. At its current speed, it will take another 20,000 years to reach the inner edge of the Oort cloud. Pluto and its neighbors are the farthest places we can realistically explore with current technology. They are the edge of what we can reach, what we can see, what we can understand without making assumptions based on distant observations. They are the boundary, the place where the solar system stops being a collection of worlds and starts being a statistical distribution of debris. And they are terrifying in their own way, not because they are violent or crushing or burning, because they are abandoned, forgotten, locked in orbits so far from the sun that the warmth you feel on Earth on a summer day is a memory, a distant echo, something that happened 1 billion miles ago and barely registers by the time it reaches them. These are the worlds at the edge. The dwarf planets and the scattered objects and the frozen moons that do not fit into any neat category. They are not planets. They are not asteroids. They are something in between, relics from a time when the solar system was still sorting itself out and deciding what would become a planet and what would be left behind. And they are waiting, frozen, silent, too far away to bother us, too strange to ignore. The solar system's attic, filled with things we do not need anymore, but cannot quite bring ourselves to throw away. And every one of them is a world unto itself, with its own geology, its own history, its own secrets frozen into the ice. Secrets we are only just beginning to uncover. We have spent the last few chapters walking through specific worlds. Venus with its acid clouds and crushing pressure, Jupiter with its century-old storm, Titan with its methane lakes, Neptune with winds that should not exist, Pluto at the frozen edge where the sun becomes a memory. Each of these places is hostile in its own distinct way, and each one kills you differently. Venus cooks you and crushes you. Jupiter irradiates you. Titan freezes you. Neptune tears you apart with winds moving faster than sound. But if you step back and look at the whole collection, a pattern emerges. These worlds are not random. They are not arbitrary. The specific ways they kill you are not accidents. They are consequences, results of physics playing out over billions of years under different starting conditions. And once you understand the underlying forces, once you see the building blocks that construct these nightmares, the entire solar system starts to make a terrible kind of sense. There are 5 categories of planetary horror, 5 fundamental ways a world can become uninhabitable. Heat, cold, pressure, wind, radiation. Every hostile environment in the solar system falls into at least one of these categories. Most fall into several. Venus is heat and pressure and toxic chemistry. Jupiter is radiation and pressure and wind. Titan is cold. Neptune is cold and wind. Mercury is heat and cold at the same time, swinging between extremes so violently that the surface cracks. Each category has its own physics, its own rules, its own way of making life impossible. Start with heat. Heat is energy, thermal energy. The random vibration of atoms and molecules bouncing around in matter. The hotter something is, the faster those atoms move. On Earth, room temperature is around 300 Kelvin, 77 degrees Fahrenheit. At that temperature, water is liquid, organic molecules are stable, proteins fold correctly, DNA holds together, life works. Increase the temperature and things start to break. At 373 Kelvin, 100 degrees Celsius, water boils, proteins denature, most enzymes stop functioning. Push higher and organic molecules start to decompose. At 600 Kelvin, most hydrocarbons break apart. At 1000 Kelvin, metals begin to glow red. At 2000 Kelvin, rock melts. At 5000 Kelvin, you are approaching the surface temperature of the Sun. Venus sits at 735 Kelvin, hot enough to melt lead, hot enough to break apart any organic molecule that touches the surface. The heat comes from the greenhouse effect, the trapping of infrared radiation by carbon dioxide in the atmosphere. Sunlight hits the surface, warms it, and the surface radiates that heat as infrared. But the carbon dioxide absorbs the infrared and traps it. The energy cannot escape. It accumulates. The temperature climbs until the rate of energy radiating out through the thin gaps in the absorption spectrum matches the rate of energy coming in from the Sun. On Venus, that equilibrium temperature is 735 Kelvin. The process is simple. The result is catastrophic. The runaway greenhouse effect is a feedback loop. More heat means more water vapor in the atmosphere. Water vapor is a greenhouse gas. More greenhouse gas means more heat. More heat means more water evaporates. The loop locks in. On Earth, the loop is broken by rain. Water vapor condenses, falls as rain, gets absorbed by oceans and rocks, and is removed from the atmosphere. On Venus, the temperature got high enough that the oceans boiled completely away. Once all the liquid water was gone, there was nothing left to break the loop. The planet cooked itself. Mercury shows the opposite problem. Mercury is closer to the Sun than Venus, but it has almost no atmosphere. During the day, the surface temperature climbs to 700 Kelvin. At night, it drops to 100 Kelvin. The difference is 600 degrees. The day side is hot enough to melt zinc. The night side is cold enough to freeze oxygen solid. The temperature swing happens because there is no atmosphere to redistribute the heat. On Earth, the atmosphere carries heat from the day side to the night side, through wind and convection. On Mercury, there is no wind. The heat stays where it lands. The result is a planet where one side bakes and the other side freezes, and the line between them is a moving boundary of thermal violence. Cold is the opposite problem. Cold is the absence of heat. When atoms stop moving, when thermal energy drains away, matter freezes, water turns to ice. Gases condense into liquids, liquids freeze into solids. At 77 Kelvin, nitrogen freezes. At 20 Kelvin, hydrogen freezes. At absolute zero, 0 Kelvin, all atomic motion stops. Nothing in the universe reaches absolute zero. The coldest natural place we have measured is the Boomerang Nebula, a cloud of gas expanding in interstellar space, sitting at about 1 Kelvin. In our solar system, the coldest surfaces are in the outer reaches of the Kuiper Belt, where sunlight is so weak it barely registers and objects cool down to around 30 or 40 Kelvin. Titan sits at 94 Kelvin. Pluto averages 41 Kelvin. Triton, Neptune's largest moon, holds the record for the coldest measured surface in the solar system at 38 Kelvin. At these temperatures, the rules change. Water stops being a liquid or a gas and becomes bedrock. Nitrogen stops being an atmospheric component and becomes a glacier. Methane, which we burn as fuel on Earth, rains from the sky. The chemistry does not stop, it just slows down. Reaction rates drop exponentially as temperature decreases. A reaction that happens in seconds at room temperature might take years at Titan's temperature. Life as we understand it cannot function. The enzymes would not work. The membranes would shatter. DNA would be frozen solid. The cold in the outer solar system comes from distance. Energy falls off with the square of the distance from the source. Double the distance from the sun, and you receive 1/4 the energy. Pluto is 40 times farther from the sun than Earth. It receives 1/1600th the solar energy. That is not enough to keep nitrogen gaseous. It is barely enough to sublimate nitrogen ice during perihelion. The sun at Pluto's distance is not a source of warmth. It is a bright dot in a black sky. The cold is absolute, unrelenting, and it has been that way for the entire history of the solar system. Pressure is force per unit area. Atmospheric pressure is the weight of the gas above you pressing down. On Earth, the atmosphere weighs 14.7 pounds per square inch at sea level. That is 1 bar, 1 atmosphere. It is the baseline we use for everything. Your body is built to handle 1 bar. Your lungs inflate against 1 bar of external pressure. Your blood stays liquid at 1 bar. Increase the pressure and things compress. Decrease it and things expand, boil, rupture. Venus has 92 bars of pressure at the surface. That is 92 times the weight of Earth's atmosphere pressing down on every square inch of surface. Stand on Venus and the air around you would feel like a fluid, thick, resistant. The pressure is enough to crush a human body, not instantly, not explosively, just steadily. Your chest would not be able to expand. Your lungs would not inflate. You would suffocate under the weight of the atmosphere. The high pressure is a direct result of the thick atmosphere. Venus has more atmosphere than Earth by a factor of 93 in total mass. All of that gas has weight. The weight presses down. The pressure at the bottom is the weight of everything above. At the other extreme, low-pressure environments like Mars create the opposite problem. Mars has an atmospheric pressure of about 6 millibars, less than 1% of Earth's. At that pressure, water cannot exist as a liquid. The boiling point of water drops so low that ice sublimates directly into vapor without melting. If you stood on Mars without a pressure suit, the moisture in your eyes and lungs would start to boil, not because it is hot, because the pressure is too low to keep it liquid at body temperature. The low pressure is a result of Mars having lost most of its atmosphere early in its history. Mars is small, its gravity is weak, it has no magnetic field to protect the atmosphere from the solar wind. Over billions of years, the solar wind stripped away most of the gas. What is left is a trace, a whisper, barely enough to call an atmosphere. Inside gas giants like Jupiter and Saturn, pressure climbs to millions of times Earth's surface pressure. At those pressures, hydrogen stops behaving like a gas. It compresses into a liquid. Compress it further, and it becomes a liquid metal, electrically conductive, flowing like mercury. The pressure is generated by the weight of the gas above pressing down on the gas below. Jupiter is massive. It has 318 times the mass of Earth. All of that mass creates gravity. Gravity pulls the gas inward. The gas at the center is supporting the weight of the entire planet. The pressure at the core is estimated at 45 million bars. At that pressure, matter behaves in ways we cannot replicate in any lab on Earth. Wind is the movement of gas driven by pressure gradients and temperature differences. On Earth, wind speeds top out around 200 miles per hour in the most violent tornadoes. On Neptune, winds reach 1,300 miles per hour. On WASP 127b, an exoplanet 1,100 light-years away, winds have been clocked at over 20,000 miles per hour. That is faster than the escape velocity of Earth. Winds moving fast enough that if they were blowing on Earth, they would launch objects into space. Wind speed is determined by the energy available to drive the motion and the resistance the atmosphere provides. More energy, faster winds. Less resistance, faster winds. Neptune has very little solar energy input. The Sun at Neptune's distance provides almost no heat, but Neptune radiates 2.6 times more energy than it receives. That internal heat creates temperature gradients. Temperature gradients drive convection. Convection drives wind. The lack of surface friction, because there is no surface, means the winds do not slow down. They just keep accelerating until the energy input balances the energy lost to turbulence and internal friction in the atmosphere itself. On exoplanets like WASP 76b, the extreme wind speeds are driven by tidal locking. The planet is so close to its star that one side always faces the star, and the other side always faces away. The day side heats up to over 4,000 degrees Fahrenheit. The night side is much cooler. The temperature difference between the two hemispheres is enormous. Gas heated on the day side expands and rises. Cool gas on the night side sinks. The pressure difference drives winds around the planet at hypersonic speeds. The winds carry heat from the day side to the night side, moderating the temperature difference slightly, but not enough to stop the process. The system is locked in. The winds will blow at those speeds for as long as the planet orbits that close to its star. Radiation is energy carried by particles or electromagnetic waves. In planetary science, radiation usually means high-energy particles, charged particles from the solar wind, cosmic rays from outside the solar system, electrons and protons trapped in magnetospheres, spiraling along magnetic field lines and slamming into anything in their path. Radiation damages matter at the molecular level. High-energy particles punch through cell membranes, break chemical bonds, ionize atoms, and create free radicals that go on to cause more damage. Enough radiation will kill you. Moderate levels cause cancer and radiation sickness. Low levels are mostly harmless because biological systems can repair the damage faster than it accumulates. Jupiter has the strongest radiation belts in the solar system. The magnetic field is 20,000 times stronger than Earth's. The field traps charged particles from the solar wind and accelerates them to high speeds. The inner radiation belts are so intense that an unshielded human standing in them would receive a lethal dose in minutes. The Juno spacecraft, which orbits Jupiter, is encased in a titanium vault to protect its electronics. Even with that shielding, Juno's orbit is designed to minimize time spent in the worst regions. The radiation is not a minor inconvenience, it is a kill zone. Europa, Jupiter's fourth largest moon, orbits inside the radiation belts. The surface receives a constant bombardment of high-energy electrons and ions. The radiation dose at Europa's surface is about 5.4 sieverts per day. For reference, a dose of 5 sieverts delivered all at once is lethal to a human. Europa delivers that dose every day. Any life on the surface would be fried. Any organic molecules would be broken apart. The only place life could survive on Europa is under the ice, shielded by kilometers of frozen water that absorbs the radiation before it can reach the ocean below. These 5 categories do not exist in isolation. They interact. High temperatures drive fast winds. Low temperatures cause atmospheres to freeze and collapse. High pressure compresses gases into liquids. Low pressure allows liquids to boil. Radiation heats atmospheres by ionizing gas molecules and depositing energy. Magnetic fields trap radiation and create belts. Gravity determines atmospheric pressure by pulling gas down toward the surface. Rotation determines wind patterns by creating Coriolis forces that deflect moving air into bands and vortices. Gravity is the thread that ties everything together. Gravity is the weakest of the 4 fundamental forces, but it is the only one that acts over unlimited range and always attracts. Every piece of matter in the universe pulls on every other piece. The strength of that pull depends on the masses involved and the distance between them. Planets are massive enough that their gravity dominates the local environment. Gravity pulls gas inward, creating atmospheres. It pulls moons into orbit. It shapes the planet into a sphere because that is the configuration where all the matter is as close to the center of mass as possible. The strength of a planet's gravity determines how much atmosphere it can hold. Earth's gravity is strong enough to hold onto nitrogen and oxygen, but not hydrogen and helium. Those lighter gases escaped early in Earth's history. Jupiter's gravity is strong enough to hold onto everything. It captured hydrogen and helium from the solar nebula and never let go. Mars's gravity is too weak. It lost most of its atmosphere. Titan's gravity is weak, but Titan is so cold that even its weak gravity is enough to hold on to nitrogen. The gas molecules are moving slowly because the temperature is low. Slow-moving molecules do not reach escape velocity as easily as fast-moving ones. Tidal forces are a consequence of gravity acting over distance. When 2 objects are close together, the side of one object facing the other experiences stronger gravity than the far side. That difference in gravitational pull stretches the object. Tidal forces are what heat Io, Jupiter's innermost large moon. Io orbits close to Jupiter. Jupiter's gravity pulls on the near side of Io more strongly than the far side. The difference stretches Io, squeezing and releasing it as it moves through its slightly elliptical orbit. The constant flexing generates heat through friction. Io is the most volcanically active body in the solar system because it is being kneaded by Jupiter's gravity. Tidal forces are also what lock moons into synchronous rotation. The moon is tidally locked to Earth. One side always faces us. The same mechanism has locked Europa, Ganymede, and Callisto to Jupiter. It has locked Titan to Saturn. It has locked Pluto and Charon to each other. Tidal locking is the end state of gravitational interaction between a planet and a moon. The system loses energy through tidal flexing until the rotation rate matches the orbital period and the flexing stops. Once locked, the configuration is stable. Atmospheric composition determines how much heat gets trapped and how the atmosphere responds to solar energy. Carbon dioxide is a greenhouse gas. It absorbs infrared radiation. An atmosphere rich in carbon dioxide traps heat. Venus is the extreme example. Earth has a small amount of carbon dioxide, about 0.04%, and that is enough to raise the surface temperature by about 33 degrees Celsius above what it would be without an atmosphere. Venus has 96% carbon dioxide. The greenhouse effect is so strong it has raised the temperature by several hundred degrees. Methane is also a greenhouse gas. Titan's atmosphere is about 5% methane. That methane absorbs infrared and keeps the surface slightly warmer than it would be otherwise. Not warm, still 94 Kelvin, but a few degrees warmer than a bare icy surface would be at Saturn's distance. The methane also participates in a chemical cycle similar to Earth's water cycle. It evaporates, condenses, rains and flows. The presence of methane in the atmosphere shapes the weather and the surface geology. Hydrogen and helium, the main components of gas giant atmospheres, are not greenhouse gases. They do not absorb infrared efficiently. The thick atmospheres of Jupiter and Saturn trap heat mostly through pressure, not through radiative absorption. The heat generated in the interior has to work its way up through thousands of kilometers of dense gas before it can radiate into space. The sheer thickness of the atmosphere acts as insulation. Planetary evolution is the process by which these conditions develop and change over time. A planet does not start out hostile, it becomes hostile. Venus probably had oceans early in its history. Mars probably had a thicker atmosphere and liquid water on its surface. Titan's methane cycle only works because the Moon is far from the Sun and cold. If Titan were closer, the methane would evaporate and be lost to space. If it were farther, the methane would freeze permanently and the cycle would stop. The habitable zone is the range of distances from a star where liquid water can exist on a planet's surface. For our Sun, that zone runs from about 0.9 to 1.5 astronomical units. Earth sits at 1 astronomical unit, right in the middle. Venus is at 0.7 astronomical units, too close. Mars is at 1.5 astronomical units, right at the edge. The habitable zone is not a guarantee of habitability. It is just the region where the temperature is right for water. Venus is in the habitable zone by some definitions, and it is the least habitable planet in the inner solar system. Mars is in the habitable zone, and it is a frozen desert. Being in the zone is necessary but not sufficient. The concept of an extreme zone is less well defined but more useful for understanding hostile worlds. The extreme zone is where conditions are so far outside the range that supports life that nothing recognizable as biology could function. Venus is in the extreme zone, so is Jupiter, so is Mercury's day side, so is Pluto. The boundaries are not sharp because different organisms have different tolerances. Extremophiles on Earth can survive temperatures up to about 400 Kelvin, pressures up to a few hundred bars, radiation doses that would kill a human, and pH levels that would dissolve metal. But even extremophiles have limits. No known organism can survive on Venus. No known organism can survive in Jupiter's atmosphere. The extreme zone is where the physics of the environment overpowers the chemistry of life. The terrifying thing is how easy it is to end up in the extreme zone. Venus and Earth started with similar conditions. Venus ended up in hell. Mars started with liquid water. Mars ended up frozen and dead. Titan has all the ingredients for interesting chemistry. It is too cold for that chemistry to do anything useful. A few degrees warmer, and Venus might have stayed habitable. A slightly stronger magnetic field, and Mars might have kept its atmosphere. A little closer to the Sun, and Titan's lakes would boil away. The margin between habitable and hostile is narrow. The feedback loops that drive a planet into the extreme zone are powerful and difficult to reverse. Our solar system is full of examples. 8 major planets, and only one of them sits in the narrow band of temperature, pressure, and chemistry that allows life. The other 7 are laboratories, test cases, demonstrations of what happens when the variables shift. Venus shows what happens when the greenhouse effect runs away. Mars shows what happens when a planet loses its atmosphere. Jupiter and Saturn show what happens when you scale up. Uranus and Neptune show what happens when you move out to the cold. Mercury shows what happens when you strip away the atmosphere entirely. Every planet is a data point. Every moon is an experiment, and every one of them teaches the same lesson. The universe does not build habitable worlds by default. It builds planets, and planets are shaped by gravity, temperature, pressure, radiation, and time. Most combinations of those variables produce something hostile. Earth is not the default. Earth is the outlier, the exception that proves the rule. And the rule is that most places in the universe are not safe. Most places will kill you. Most places are defined by extremes that human biology was never designed to handle. The solar system is not trying to teach us humility. It is not trying to teach us anything. It just is. A collection of worlds assembled from the same materials under slightly different conditions, evolving over billions of years into the configurations we see today. Some are hot, some are cold, some are thick with atmosphere, some are airless. Some have storms that have been running since before humans existed. Some are geologically dead, their surfaces unchanged for billions of years. Each one is a consequence of physics. Each one is a result of the same fundamental forces acting under different initial conditions, and each one is a reminder that the Earth, the one planet where you can step outside without a suit and not die immediately, is an accident. A fortunate configuration of variables that happen to land in the narrow range where liquid water stays stable, where temperatures allow organic chemistry, where a magnetic field shields the surface from radiation, where plate tectonics recycle carbon and regulate the climate over geologic timescales. That configuration is rare. The solar system tried 8 times to make a major planet, and it succeeded once. The odds are not good. Which brings us back to the question that has been sitting in the background this entire time. If Earth is the exception, if habitable worlds are rare, if most planets are hostile by default, what does that tell us about the universe beyond our solar system? What does that tell us about the billions of exoplanets we have discovered in the last few decades? What does that tell us about the prospects for finding life elsewhere? The solar system is a laboratory. It is a controlled experiment where we can study planetary formation, atmospheric evolution, and the limits of habitability in detail. Every world we have explored, every probe we have sent, every measurement we have taken is data, evidence, a piece of the puzzle. And the picture that emerges from that data is not comforting, it is not hopeful, it is just honest. Most places are hostile, most worlds are extreme, and the handful of places where life could exist are buried under ice, or hidden in subsurface oceans, or sitting at the edge of the habitable zone, barely clinging to the conditions that make biology possible. That is the nature of extremes. They are not exotic. They are not rare. They are the default state of planetary systems. And Earth, with its breathable air, and its liquid oceans, and its stable climate, is the strange one. the one that does not fit, the one that defies the pattern. And if we want to understand why Earth turned out the way it did, if we want to figure out how to recognize other habitable worlds around other stars, we need to understand the extremes first. We need to map the boundaries. We need to know what kills planets and what keeps them alive. And the only way to do that is to study the ones that failed, the ones that went wrong, the ones that ended up in the extreme zone and never came back. Our solar system is full of those failures, and every one of them has something to teach us. We have spent the last several chapters walking through a catalogue of nightmares, worlds that crush you, burn you, freeze you, irradiate you, or tear you apart with winds moving faster than the speed of sound. Venus and Jupiter and Neptune and Pluto, each one a demonstration of how badly planetary formation can go if the variables shift even slightly away from the configuration that produced Earth. And the obvious question, the one that should have been nagging at you this entire time, is why any of this matters. Why do we care about the temperature on Venus, or the wind speed on Neptune, or whether Titan has methane lakes? The answer is that these worlds are not just death traps. They are laboratories, natural experiments running on scales and timescales we could never replicate on Earth. Every hostile planet in the solar system is teaching us something about how planets work, how atmospheres evolve, how climates stabilize or collapse, and what the boundaries of habitability actually are. Venus is not just a warning about runaway greenhouse effects. It is a controlled case study in atmospheric chemistry under extreme conditions. Jupiter is not just a radiation-soaked storm factory. It is a window into how gas giants form and what happens when you scale planetary dynamics up to absurd sizes. Titan is not just a frozen methane swamp. It is the only other place in the solar system with stable liquid on its surface and an active weather cycle, and studying it tells us things about Earth we would never learn by staying home. The solar system is 8 major planets, 5 recognized dwarf planets, over 200 moons, millions of asteroids, billions of comets, and not one of them aside from Earth would let you survive on its surface without a pressure suit and a heating system and a radiation shield and a carefully calibrated supply of breathable air. That is the data set. That is the sample size. 8 attempts to build a major planet, and only one of them landed in the narrow range of conditions where life as we understand it could start and keep going. The other 7 are failures by that metric, but they are not useless failures, they are instructive failures. Each one shows us a different way the process can go wrong, and each one gives us a reference point for understanding planets around other stars. Because here is the thing, we are not stuck with 8 planets anymore. As of early 2025, astronomers have confirmed the existence of over 6,000 planets orbiting other stars. 6,000. That number has been climbing steadily since the first exoplanet around a Sun-like star was discovered in October 1995. The planet was called 51 Pegasi b, and it was nothing like anything in our solar system. A gas giant roughly half the mass of Jupiter, orbiting its star once every 4 days. 4 days. For comparison, Mercury, the closest planet to our Sun, takes 88 days to complete one orbit. 51 Pegasi b was so close to its star that its surface temperature was estimated at over 1,000 degrees Celsius. It was a hot Jupiter, a category of planet that should not exist according to the models astronomers were using at the time. Hot Jupiters were a problem. Gas giants are supposed to form far from their stars, out in the cold regions where water and methane and ammonia can freeze into ice and provide enough solid material to build a massive core. Once the core gets large enough, it starts pulling in hydrogen and helium from the surrounding nebula, and you end up with a gas giant. That process only works in the cold outer regions of a planetary system. So how did a Jupiter-sized planet end up orbiting so close to its star that it completes a lap in 4 days? The answer, worked out over the next few years, is migration. Planets do not stay where they form. Gravitational interactions with the disk of gas and dust they form from, or with other planets in the system, can cause them to drift inward or outward over time. Hot Jupiters formed far out, then migrated inward, spiraling closer to their stars until they settled into tight orbits, where the inward pull of drag from the remaining gas balanced the outward push of their orbital momentum. Once the gas cleared, the planets were stuck, left behind in orbits that make no sense unless you account for their history. That discovery rewrote the rules. Planets are not static. They move, they migrate, they interact. The configuration you see today is not the configuration that existed 1 billion years ago, or that will exist 1 billion years from now. The solar system looks stable because we are watching it over human timescales, decades and centuries, and on those timescales, nothing moves enough to notice. But zoom out to millions or billions of years, and the planets are drifting, orbits are shifting, moons are spiraling inward or outward. The whole system is dynamic, and the same is true for every planetary system around every star. The 6,000 confirmed exoplanets we have found so far are not a complete census. They are a biased sample. Most of them were detected using 2 methods: transit photometry, where you watch a star and wait for a planet to pass in front of it, blocking a tiny fraction of the star's light, and Doppler spectroscopy, where you measure the star's wobble caused by the gravitational tug of an orbiting planet. Both methods work best for large planets orbiting close to their stars. Large planets block more light. Close-in planets transit more often. Large planets tug harder on their stars. Close-in planets cause faster wobbles that are easier to detect. The result is that the exoplanet catalogue is full of hot Jupiters, hot Neptunes, and super-Earths in tight orbits. Not because those are the most common types of planets, because those are the easiest types to find with current technology. Super-Earths are planets with masses between Earth and Neptune, roughly 1 to 10 times Earth's mass, radii between 1 and 4 times Earth's radius. They are everywhere. The most common type of planet in the galaxy as far as we can tell, and they are completely absent from our solar system. We do not have a single planet in that mass range. Earth is the largest rocky planet we have. Uranus and Neptune are ice giants, more than 14 times Earth's mass. There is nothing in between. That gap is one of the biggest mysteries in planetary science. Why did our solar system skip the super-Earth phase when every other system seems to have at least one? The leading theory involves Jupiter. Jupiter formed early, within the first few million years of the solar system's history. It grew fast, pulling in gas and becoming a massive gravitational anchor in the outer system. That anchor disrupted the flow of material in the protoplanetary disk, creating a gap that prevented solid material from migrating inward to the region where super-Earths would have formed. Without that material, the inner solar system was left with only the rocky planets we see today. If Jupiter had formed later, or farther out, or not at all, the inner solar system might look completely different. We might have a super-Earth where the asteroid belt is now, or 2 or 3 of them, packed into tight orbits closer to the Sun. The absence of super-Earths in our solar system is an accident, a quirk of timing and dynamics that left us with a configuration that is, as far as we can tell, unusual. That absence matters because it means we have no local examples to study. We cannot send a probe to a super-Earth. We cannot measure its atmospheric composition or map its surface or figure out whether it has a magnetic field. We have to infer everything from distant observations, and those observations are limited. We can measure the planet's mass by watching how much it tugs on its star. We can measure its radius by watching how much light it blocks during a transit. From mass and radius, we can calculate density, and density tells us whether the planet is rocky, icy, or gas-rich. But that is it. We cannot see the surface. We cannot sample the atmosphere directly. We can only build models and hope they are right. The models say super-Earths come in two main flavors: rocky super-Earths with thick atmospheres, possibly rich in hydrogen and helium left over from the protoplanetary disk, and mini-Neptunes, slightly larger, with thick envelopes of gas surrounding a rocky or icy core. The boundary between the two types is not sharp. It is a continuum. But the distinction matters because rocky super-Earths might be habitable if they are the right distance from their stars. Mini-Neptunes probably are not. Too much gas, too much pressure, no solid surface to stand on. The challenge is that from our vantage point, looking at these planets from hundreds or thousands of light years away, it is hard to tell which type you are looking at. This is where the solar system becomes useful. We have Neptune, we have Uranus. Both are ice giants with thick hydrogen-helium envelopes. Both have been studied up close by Voyager 2. We know their atmospheric composition. We know their internal structure, or at least we have good models based on Voyager's gravity measurements. We know how their magnetic fields behave and how their weather systems work. That knowledge gives us a baseline. When we look at a mini-Neptune around another star, we can compare it to Uranus or Neptune and make educated guesses about what is happening in its atmosphere. When we model the internal structure of a super-Earth, we can use Neptune's density and composition as a reference point. The ice giants are not just interesting in their own right, they are templates. Rosetta Stones for understanding a class of planet that is common in the galaxy but missing from our immediate neighborhood. The same logic applies to gas giants. Jupiter and Saturn are not just local curiosities. They are the only gas giants we have ever studied in detail. We know how their atmospheres circulate. We know how their magnetic fields trap radiation. We know how their storms form and evolve. That knowledge is directly applicable to hot Jupiters. When we detect a hot Jupiter with wind speeds of several thousand miles per hour, we can look at Jupiter's wind patterns and ask what would happen if you moved Jupiter closer to the Sun and heated it up. The answer, based on models informed by Jupiter's observed behavior, is that you get faster winds, more violent storms, and a day side that is significantly hotter than the night side. The models match the observations. The solar system's gas giants are teaching us how gas giants work everywhere. Titan is another template, the only moon with a thick atmosphere, the only place aside from Earth with stable liquid on its surface and an active weather cycle. Studying Titan tells us what happens when you take a world with organic chemistry and freeze it at 94 Kelvin. The methane cycle on Titan mirrors Earth's water cycle almost exactly. Liquid evaporates, vapor rises, clouds form, rain falls, liquid collects in lakes and rivers, the cycle repeats. The only difference is the chemical species involved, methane instead of water. But the physics is the same. Titan is a controlled experiment in climate dynamics at low temperatures, and the lessons learned there are applicable to exoplanets in the outer edges of habitable zones around dim stars. The habitable zone is the range of distances from a star where liquid water can exist on a planet's surface. For our Sun, that zone runs from about 0.9 to 1.5 astronomical units. Earth sits at 1. Venus is at 0.7, too close. Mars is at 1.5, right at the edge. The boundaries are not sharp because they depend on the planet's atmosphere. A thick atmosphere with a strong greenhouse effect can extend the habitable zone outward. A thin atmosphere, or no atmosphere at all, shrinks it inward. The definition is also split into conservative and optimistic versions. The conservative definition is stricter, requiring conditions where liquid water is stable over geologic timescales. The optimistic definition is broader, allowing for temporary or localized liquid water. The choice of definition matters because it affects how many potentially habitable planets we think exist in the galaxy. Current estimates, based on data from the Kepler Space Telescope and other surveys, suggest that about 1 in 5 Sun-like stars has an Earth-sized planet in the habitable zone. That sounds promising until you do the math. There are roughly 200 billion stars in the Milky Way. About 10% of them are Sun-like. That gives you 20 billion Sun-like stars. 1 in 5 of those has a habitable zone Earth-sized planet. 4 billion planets, 4 billion potential Earths in our galaxy alone, except most of those planets are not Earth. They are Earth-sized and Earth temperature, but that does not make them habitable. Venus is Earth-sized, it is not habitable. Mars is on the edge of the habitable zone. It is a frozen desert. Being the right size and the right distance is necessary, but not sufficient. The question is what else matters? Magnetic fields? Probably. Earth has a strong magnetic field generated by convection in its liquid iron core. The field shields the atmosphere from the solar wind. Without it, the solar wind would strip away the atmosphere over millions of years, the way it stripped away most of Mars's atmosphere. Plate tectonics, possibly. Plate tectonics recycle carbon between the atmosphere and the mantle, regulating the greenhouse effect over geologic timescales. Without plate tectonics, carbon builds up in the atmosphere and you get a runaway greenhouse. Or carbon gets locked into rocks and you get a frozen planet. Moons, maybe. Earth's moon stabilizes the planet's axial tilt, preventing wild swings in climate that would make life difficult. Without the moon, Earth's tilt could vary by tens of degrees over millions of years, causing extreme seasonal changes. We do not know which of these factors are essential and which are just helpful. We have a sample size of one habitable planet, one data point. That is not enough to build a reliable model. So we look at the other planets in the solar system and try to figure out what went wrong. Why is Venus a runaway greenhouse instead of a second Earth? Why did Mars lose its atmosphere? Why is Titan covered in organic molecules but shows no signs of life? Every failed planet is a clue. Every hostile world is a lesson in what not to do if you want to stay habitable. The technological challenges of studying these worlds are enormous. Sending a probe to Pluto took 9.5 years and required a gravity assist from Jupiter. Sending a probe to Uranus or Neptune would take even longer. Sending a probe to any of the outer Kuiper Belt objects would take decades. And those are the easy targets. Those are places we can reach with current propulsion technology if we are patient. Studying exoplanets requires different tools. Telescopes, not spacecraft. Spectroscopy, not direct sampling. We cannot send a probe to a planet orbiting another star. The distances are too great. The travel times are measured in thousands or tens of thousands of years with any propulsion system we can build today. The James Webb Space Telescope is the most powerful tool we have for studying exoplanets. Webb can analyze the light from a planet's atmosphere as it transits its star. The starlight passes through the planet's atmosphere and certain wavelengths get absorbed by molecules in that atmosphere. By measuring which wavelengths are missing, astronomers can identify what gases are present: water vapor, carbon dioxide, methane, oxygen. Each molecule has a unique spectral fingerprint. Webb has already detected water vapor in the atmospheres of several hot Jupiters. It has measured the temperature of super-Earths and mini-Neptunes. It has started to build a catalogue of exoplanetary atmospheres, and that catalogue is growing every year. The next generation of telescopes will go further. The extremely large telescope, currently under construction in Chile, will have a mirror 39 meters across. That is 4 times the diameter of the largest telescopes operating today. The Habitable Worlds Observatory, a proposed NASA mission for the 2040s, is designed specifically to image Earth-like planets around nearby stars and analyze their atmospheres for signs of life. These instruments will not just detect exoplanets, they will characterize them. Tell us what they are made of, what their atmospheres look like, whether they have oceans or continents or clouds, whether there is any indication of biological activity. The search for life is the ultimate goal, but it is not the only goal. Even if we find 100 Earth-sized planets in habitable zones and none of them show any signs of life, that is useful data. It tells us that life is rare, that Earth is even more unusual than we thought, that the conditions required for biology to start and keep going are stricter than the optimistic estimates suggested. It narrows the parameter space, it refines the models. Every observation, whether it confirms our expectations or contradicts them, moves the field forward. The philosophical implications are unavoidable. For most of human history, Earth was the only world we knew. The sky was lights. The planets were wandering stars. We had no concept of other worlds as places, as environments, as systems with their own rules. Then we built telescopes and spacecraft and started exploring, and the picture changed. The solar system is not a collection of lights. It is a collection of worlds, each one as real and as complex as Earth, each one shaped by the same physical laws, each one a consequence of the same processes that built our home. And most of them are hostile. Most of them would kill us in seconds or minutes. The universe is not designed for human comfort. Now we know there are thousands of other systems out there, thousands of other collections of worlds orbiting other stars, and the data so far suggests that our solar system is not typical. The mix of planets we have, the sizes, the orbits, the spacing, none of it matches the most common configurations we see around other stars. We do not have hot Jupiters. We do not have super-Earths. Our gas giants are far from the Sun, not close in. Our rocky planets are small, not massive. The solar system, it turns out, is somewhat mundane, an outlier, a configuration that does not show up very often in the galactic census. That raises questions. If our solar system is unusual, does that make Earth more unusual? Is the configuration of planets we have a prerequisite for habitability, or just one possible path? Could a system with a hot Jupiter and a super-Earth in the habitable zone produce life? Could a planet orbiting a red dwarf star, tidally locked with one side always facing the star, support biology? We do not know. We have one example. One planet where life started and survived and diversified over billions of years. One data point. The TESS-KEK survey, a collaboration between NASA's Transiting Exoplanet Survey satellite and the Keck Observatory in Hawaii, recently released a catalogue of 126 extreme and exotic worlds, planets with highly eccentric orbits, planets with densities that do not match any model, planets orbiting binary stars, planets so close to their stars that their surfaces are molten. The catalogue was built from over 13,000 measurements of stellar wobbles, tiny shifts in starlight caused by orbiting planets tugging on their host stars. Every entry in that catalogue is a planet that challenges our understanding. Every entry is a world that does not fit neatly into the categories we built based on the solar system. The textbooks are being rewritten yearly. That is not an exaggeration. Planetary science as a field is moving so fast that any textbook more than a few years old is already out of date. New discoveries come in faster than the models can keep up. Every year, new categories of planets are proposed. New formation mechanisms are suggested. New boundaries are drawn and then erased. The field is in a state of productive chaos, and the solar system is the anchor. The one place we can go and measure things directly. The one place we can send spacecraft and get high-resolution data and test our models against reality. The 8 planets, the moons, the dwarf planets, the asteroids, all of it is a laboratory, a testing ground, a reference library. And every hostile world, every extreme environment, every planet that would kill you in under a minute is teaching us something about how planets work and what makes them habitable or hostile. Venus teaches us about greenhouse effects. Mars teaches us about atmospheric loss. Jupiter teaches us about gas giant dynamics. Titan teaches us about organic chemistry at low temperatures. Neptune teaches us about internal heat and wind speeds. Pluto teaches us about the Kuiper belt and the conditions at the edge of planetary systems. We are not exploring these worlds because they are easy or because they are friendly. We are exploring them because they are there, and because every measurement we take, every image we capture, every spectrum we analyze adds to the dataset. And the dataset is how we figure out what is normal and what is strange, what is common and what is rare, what is possible and what is forbidden by the laws of physics. The solar system is not just our neighborhood, it is our classroom, and the lessons it teaches are not comfortable. They are not reassuring, but they are honest. The future of planetary science depends on going deeper, sending more missions, building better telescopes, analyzing more spectra, cataloging more exoplanets, finding the super-Earths and the mini-Neptunes and the hot Jupiters and the cold Jupiters and everything in between, measuring their atmospheres, mapping their surfaces, looking for patterns. The goal is not just to find life, though that would be the discovery of the millennium. The goal is to understand the rules, to figure out what makes a planet habitable and what makes it hostile, to learn how planetary systems form and evolve and stabilize, to take the lessons from Venus and Mars and Titan and Pluto and apply them to worlds we will never visit in person but can study from a distance. And all of that starts here, in the solar system, with the 8 planets and their moons and the dwarf planets at the edge, with the storms on Jupiter and the lakes on Titan and the frozen plains of Pluto and the crushing heat of Venus. Every one of them a laboratory, every one of them a lesson, every one of them a piece of the puzzle. We are learning how to read planets, how to look at a distant dot orbiting another star and figure out what it is made of, what its atmosphere is like, whether it has water, whether it could support life. And the Rosetta Stone for all of that is right here, the solar system, the collection of worlds we have been living alongside our entire history and only recently started to understand. The discoveries keep coming, the models keep evolving, the boundaries keep shifting. And the one constant is that the universe is bigger and stranger and more diverse than anyone expected. Our solar system, mundane as it might be compared to the extremes out there, is still the only one we can study in detail, the only one we can touch. And every hostile world within it is teaching us how to recognize the rare exceptions, the handful of planets in the galaxy where the variables landed just right and life had a chance. That is the lesson from the abyss. The solar system is not a collection of destinations. It is a field guide, a manual for reading planets. And the more we study the extremes, the better we get at recognizing the boundaries, at understanding what Earth is and why it is so rare, at preparing ourselves for what we might find when we finally turn our telescopes toward the right star and spot a pale blue dot that looks just different enough to be worth a second look. And that second look, that moment of recognition when we find another world that might just possibly be something like home, will only happen because we spent decades staring at the worlds that are nothing like home. Learning from Venus, learning from Mars, learning from Pluto at the frozen edge. The abyss teaches by showing you what does not work. And once you understand what does not work, you start to see the narrow path that does. The solar system has been teaching us that path for 50 years. And we are finally starting to listen. We have spent the last 9 chapters walking through the solar system's greatest hits, the planets that crush you, burn you, freeze you, and strip the electrons off your atoms one at a time. Venus with its lead-melting surface, Jupiter with its radiation belts and storms that have outlasted empires, Neptune with winds that should not exist, Pluto at the frozen edge where the sun is just a bright dot and the nitrogen snows down in drifts that sit unchanged for millions of years. And through all of it, one question has been sitting in the background, waiting. If this is what our solar system looks like, if these are the worlds that formed from the same cloud of gas and dust that made Earth, what horrors are waiting around other stars? The answer is that we are about to find out. Not in some distant theoretical future, now. Over the next 10 to 15 years, a new generation of telescopes is going to come online, instruments so powerful that they will not just detect exoplanets the way we have been doing for the last 30 years. They will see them, image them directly, analyze their atmospheres in detail, tell us what they are made of, what their weather looks like, whether there is water, whether there are clouds, whether the chemistry happening in those atmospheres looks anything like the chemistry that supports life on Earth. And the terrifying part, the part that should make you slightly uncomfortable if you think about it too long, is that based on everything we have learned from studying our own solar system, most of what we find is going to be worse than anything we have seen so far. Our solar system is tame. That is the conclusion you have to draw if you look at the data honestly. Yes, Venus is a runaway greenhouse. Yes, Jupiter will irradiate you to death. Yes, Neptune has winds moving at 1,300 miles per hour. But Venus is not tidally locked to the sun, with one side in permanent daylight and the other in permanent darkness. Jupiter is not so close to the sun that its atmosphere is being stripped away in real time by stellar wind. Neptune is not orbiting so tightly that it completes a full orbit in less than a day, heated to the point where its surface glows red. We know these configurations exist because we have found them. Hot Jupiters orbiting so close to their stars that they are slowly evaporating. Super-Earths with surface pressures hundreds of times higher than Venus. Planets with atmospheres made of vaporized rock. Planets with clouds made of molten glass that rains sideways in winds clocked at thousands of miles per hour. Planets where the day side is hot enough to melt iron and the night side is cold enough to freeze carbon dioxide, and the boundary between the two is a permanent storm front circling the planet like a scar. These are not theoretical. These are real planets, detected and confirmed, orbiting real stars within a few hundred light-years of Earth, and they are just the beginning. The planets we have found so far are the easy ones, the big ones, the ones close to their stars, the ones whose transits block enough light or tug their stars hard enough that we can detect them with current instruments. The Kepler Space Telescope, which ran from 2009 to 2018, found over 2,700 confirmed exoplanets. TESS, the Transiting Exoplanet Survey satellite, launched in 2018, has found over 7,000 candidates and confirmed hundreds. The James Webb Space Telescope, operational since 2022, has started analyzing their atmospheres. But all of these instruments are working at the edge of their capabilities. They are optimized for brightness, for sensitivity, for detecting faint signals against noisy backgrounds. They are not optimized for imaging. They are not designed to take pictures of planets directly. That is about to change. NASA's Nancy Grace Roman Space Telescope is scheduled to launch in 2027. Roman is a survey telescope, built to observe huge swaths of sky quickly and efficiently. Its primary mirror is the same size as Hubble's, 2.4 meters, but its field of view is 100 times larger. Where Hubble takes detailed images of small patches of sky, Roman will take wide-angle surveys, covering areas the size of 100 full moons in a single shot. Its mission is to search for exoplanets using gravitational microlensing, a technique that works by watching for the brief brightening of a distant star when a planet passes in front of it and bends the starlight with its gravity. Microlensing is sensitive to planets at all distances from their stars, not just the close-in ones that transit detection favors. It can find planets in wide orbits, planets in the habitable zone, planets around faint stars, planets that would be invisible to any other method. Roman is expected to discover over 100,000 new exoplanets in its first 5 years of operation. 100,000. That is not a typo. That is the estimate. The catalogue is about to explode, but discovery is only the first step. Once you know a planet is there, you need to figure out what it is. Mass, radius, density, atmospheric composition, surface temperature. All of that requires follow-up observations with instruments designed for characterization, not just detection. And this is where the next generation of space telescopes comes in. The Habitable Worlds Observatory, currently in the planning stages at NASA with a target launch date sometime in the 2040s, is being designed specifically to image Earth-like planets around Sun-like stars and analyze their atmospheres for signs of life, not hints of life, not ambiguous chemical signals that could be biological or could be geological, actual biosignatures. Oxygen and methane together in ratios that scream metabolism. Oxygen and nitrous oxide, which on Earth is primarily produced by bacteria. Dimethyl sulfide, a compound made almost exclusively by living organisms. The telescope will use a coronagraph, a device that blocks the light from the star so the much fainter light from the planet can be detected. The coronagraph on HWO will be thousands of times more advanced than anything currently in operation, capable of suppressing starlight to the point where planets as small and as dim as Earth become visible. The technical challenges are enormous. An Earth-sized planet orbiting a Sun-like star at 1 astronomical unit, the distance Earth orbits our Sun, is about 10 billion times fainter than the star. 10 billion. Imagine trying to see a firefly hovering next to a searchlight from 1,000 miles away. That is the problem. The coronagraph has to block the searchlight without blocking the firefly. It has to do this for dozens of stars, each one at a slightly different distance, each one with slightly different brightness. And it has to do it well enough that the light from the planet can be collected and split into a spectrum so we can analyze which wavelengths are present and which are missing. From that spectrum, we can identify the molecules in the planet's atmosphere: water vapor, carbon dioxide, oxygen, methane, ozone. Each one leaves a fingerprint in the light. Each fingerprint tells us something about the planet's chemistry and climate and possibly its biology. If HWO works, and there is every reason to think it will because the technology is already being tested on smaller scales, we will have direct images of habitable zone planets around nearby stars, not artists' renditions, not models, actual photographs. Pale blue dots, or pale orange dots, or pale green dots, depending on what gases are in their atmospheres and what kind of surface they have. We will be able to watch them over the course of months or years and see if they have seasons, see if cloud patterns change, see if there are continents or oceans or ice caps. We will be able to build maps, not detailed maps. The resolution will not be good enough for that. But maps showing large-scale features, light and dark regions, polar caps, equatorial bands, enough to start answering the question of what these worlds actually look like. And then there are the ground-based telescopes. The extremely large telescope, currently under construction in Chile's Atacama Desert, will have a primary mirror 39 meters across. 39 meters. That is 128 feet. The mirror is so large, it has to be assembled from 798 hexagonal segments, each one individually controlled by actuators that adjust its position thousands of times per second to compensate for atmospheric distortion. The ELT will be the largest optical telescope ever built, and it will be powerful enough to image planets directly in the thermal infrared, not reflected light, heat. Planets glow faintly in the infrared because they radiate the heat they absorb from their stars or generate internally. That glow is much dimmer than the reflected light, but it is also easier to separate from the star's light because stars are much brighter in visible wavelengths than in infrared. The contrast ratio is better. The ELT, combined with adaptive optics that correct for the blurring caused by Earth's atmosphere, will be able to image super-Earths and possibly terrestrial planets around the nearest stars. The resolution will not be enough to see surface details, but it will be enough to measure temperature, detect weather patterns, and analyze atmospheric composition. Europe's Plato mission, the Planetary Transits and Oscillations of Stars satellite, is scheduled to launch in 2026. Plato will monitor hundreds of thousands of bright stars, looking for transits and measuring the tiny oscillations in brightness caused by sound waves moving through the star's interiors. Those oscillations tell you the star's mass, radius, and age, and knowing the star's properties lets you calculate the planet's properties with much higher accuracy. Plato is designed to find terrestrial planets in habitable zones around sun-like stars, the kind of planets that could have liquid water on their surfaces and stable climates over billions of years. It is the next step beyond TESS, more sensitive, more precise, more focused on the stars that are most like our own sun. ESA's Ariel mission, the Atmospheric Remote Sensing Infrared Exoplanet Large Survey, launches in 2029. Ariel will conduct a chemical census of exoplanet atmospheres, observing 1,000 planets across a wide range of masses, temperatures, and compositions. It will use transit spectroscopy, watching planets as they pass in front of their stars, and analyzing the starlight that filters through their atmospheres. The light that makes it through tells you what molecules are present. The light that gets absorbed tells you what is missing. Ariel will measure water vapor, carbon dioxide, methane, ammonia, and dozens of other compounds, building a database of atmospheric compositions that astronomers can use to classify planets and understand the chemistry happening in their atmospheres. It is the first mission designed specifically to study exoplanet atmospheres in bulk, not just a few interesting targets, but a statistically significant sample that covers the full range of planetary types. Put all of this together and you get a cascade of discovery. Roman finds the planets. Plato refines the properties. Webb and HWO analyze the atmospheres. Ariel builds the database. The ELT and other ground-based telescopes image the closest and brightest targets. Within the next 15 years, we will go from knowing that exoplanets exist to understanding what they are made of, how their climates work, and whether any of them show signs of life. That is not incremental progress. That is a revolution. And the solar system is the training ground. Every measurement we have made of Venus or Jupiter or Titan or Pluto has taught us how to interpret the data we are about to receive from worlds we will never visit in person. The catalogue of extreme exoplanets is already disturbing. WASP-12b, a hot Jupiter so close to its star that it completes one orbit every 1.1 days, is being slowly torn apart by tidal forces. The planet is egg-shaped, stretched by the star's gravity, and it is losing mass at a rate of about 6 billion tons per second. 6 billion tons per second. The material is being pulled off the planet and onto the star in a stream of hot gas. The planet is evaporating in real time, and in about 10 million years it will be gone entirely, consumed by its star. We are watching a planet die. Kepler-70b and Kepler-70c are planets orbiting a star that has already passed through its red giant phase. When the star expanded, it swallowed its inner planets, vaporized them, and then contracted back down to a white dwarf. The two planets we see now are the survivors. They orbit so close to the white dwarf that their surface temperatures exceed 3,000 degrees Celsius. Hot enough to vaporize rock. Hot enough that the planets themselves are glowing. They are not reflecting light from the star. They are generating their own light from the heat. They are embers, burnt remnants of worlds that used to orbit farther out, dragged inward as the star died, stripped of their atmospheres, cooked down to bare cores of rock and metal. 55 Cancri E is a super-Earth orbiting a Sun-like star about 40 light-years away. The planet is twice the size of Earth and 8 times more massive, and it orbits so close to its star that one side is in permanent daylight. The day side is hot enough to melt rock. Spectroscopic observations suggest the atmosphere might contain vaporized silicates, rock vapor, forming clouds of molten glass. The night side is cooler, possibly solid, and the boundary between the two is a zone of constant volcanic activity where molten rock flows from the day side to the night side, cools, solidifies, and is then pushed back toward the day side by thermal expansion. The entire planet is a lava lamp, a sphere of molten rock circulating under a sky made of glass clouds. HD 8615b is one of the most extreme exoplanets ever discovered. It is a hot Jupiter orbiting a star slightly larger and hotter than the Sun. The planet's atmosphere is being stripped away by intense stellar radiation. The escaping gas forms a comet-like tail stretching millions of miles behind the planet, visible in ultraviolet light. The tail is made of hydrogen, the lightest element, blown off the planet by the stellar wind. Heavier elements like oxygen and carbon are also escaping, but more slowly. The planet is losing its atmosphere at a rate fast enough that in a few 100 million years it will be reduced to a bare rocky core, a hot Neptune turned into a hot super-Earth by the relentless bombardment of radiation. GJ1214b is a rocky planet orbiting a red dwarf star about 48 light-years away. Red dwarfs are the most common type of star in the galaxy, making up about 70% of all stars. They are small, dim, long-lived, and they have a nasty habit of producing massive solar flares that bathe their planets in radiation. GJ1214b orbits close enough to its star that it is tidally locked, one side always facing the star, the other always facing away. The day side is hot, the night side is cold, and the planet has no atmosphere. Spectroscopic observations show no signs of water vapor, carbon dioxide, methane, or any other gas. The atmosphere has been stripped away, probably by flares, leaving a bare rock with a temperature difference of hundreds of degrees between day and night. The planet is a warning. Red dwarfs might be common, but their planets might not be habitable even if they are in the right distance range for liquid water. Then there are the rogue planets, planets that do not orbit any star. They were either ejected from their home systems by gravitational interactions with other planets, or they formed in isolation from collapsing clouds of gas that were not massive enough to ignite fusion. Rogue planets are invisible unless they pass in front of a background star and cause a microlensing event, or unless they are still warm enough from formation to glow faintly in the infrared. Estimates suggest there could be billions of rogue planets in the Milky Way, possibly outnumbering stars. They drift through interstellar space in complete darkness, with no sunlight, no heat source, no energy input except the faint warmth leaking out of their interiors. Surface temperatures would be a few tens of Kelvin, colder than Pluto. Atmospheres, if they exist, would be frozen solid, lying on the surface as snow. These are worlds where the concept of day and night does not apply because there is no star, just eternal darkness, eternal cold, drifting through the void forever. The question we have to ask is why we care. Why does it matter that there are planets out there being torn apart by their stars, or cooked to the point where rock vaporizes, or frozen in permanent darkness? The answer is the same reason we care about Venus and Jupiter and Pluto. They are data. Every extreme planet is a test case. Every hostile environment tells us something about the limits of planetary systems, the range of possible configurations, the boundaries between what can exist and what cannot. When we find a planet with an atmosphere made of vaporized rock, that tells us something about atmospheric chemistry at high temperatures. When we find a planet being stripped by stellar wind, that tells us something about the interaction between stars and planets. When we find a rogue planet, that tells us something about how planetary systems form and how they can fall apart. And all of this feeds back into the search for habitable worlds, because the only way to recognize a habitable planet is to understand what makes most planets uninhabitable. If every planet we found looked like Earth, the search would be easy. But that is not the universe we live in. Most planets are hostile. Most planets are extreme. The habitable ones are rare, and recognizing them requires understanding the full spectrum of planetary environments, from the ones that are almost habitable to the ones that are so far into the extreme zone that they barely qualify as planets anymore. The solar system is our reference library. The 8 planets and their moons are the only worlds we can study in detail with spacecraft, the only worlds we can sample directly, the only worlds where we can send a probe and get high-resolution images and measure atmospheric composition at multiple altitudes and map the surface at meter-scale resolution. Every mission to Venus or Jupiter or Titan or Pluto adds to that library. Every measurement refines the models. Every observation gives us a better understanding of how planets work, how atmospheres evolve, how climates stabilize or collapse. And when we point our telescopes at exoplanets and try to figure out what they are made of, we compare them to the solar system. We look for analogues. We ask whether this exoplanet looks more like Venus or more like Earth, whether that hot Jupiter looks more like Jupiter heated up or something entirely different, whether this super-Earth looks like a scaled-up rocky planet or a scaled-down ice giant. The comparisons are not always clean. Exoplanets do things that planets in our solar system do not, but the framework is there. The physics is the same. Gravity works the same way everywhere. Thermodynamics does not change from star to star. Atmospheric circulation follows the same equations on an exoplanet as it does on Jupiter. The details differ, the numbers change, but the underlying rules are universal. And the only reason we know those rules is because we have spent decades studying the planets in our own system. Proxima Centauri b is the closest known exoplanet to Earth. It orbits Proxima Centauri, a red dwarf star about 4.2 light-years away. The planet is roughly Earth-sized, possibly rocky, and it orbits in the star's habitable zone. On paper, it is one of the best candidates for finding life. But Proxima Centauri is a flare star. It produces massive flares, bursts of radiation that can double the star's brightness in a matter of minutes. Those flares hit Proxima b with enough energy to strip away any atmosphere the planet might have had, unless the planet has a strong magnetic field to deflect the radiation. We do not know if it has a magnetic field. We do not know if it has an atmosphere. We do not even know for sure that it is rocky. What we do know is that it is the closest Earth-sized planet in a habitable zone, and it is the first place we will look when the next generation of telescopes comes online. If Proxima b has an atmosphere, the extremely large telescope will be able to detect it. If the atmosphere contains oxygen, HWO will be able to measure it. If the oxygen is present in combination with methane or other gases that suggest biological activity, that will be the most important discovery in human history. And if the atmosphere is gone, stripped away by flares, that will also be important. It will tell us that planets around red dwarfs, the most common type of star, are probably not habitable unless they have unusually strong magnetic fields or some other way to protect themselves from radiation. The Great Magellan Telescope, under construction in Chile with a projected completion date in the early 2030s, will have a primary mirror 25 meters across. It will be capable of surveying 5 to 7 Earth-like planets for oxygen in their atmospheres. The ELT, with its larger mirror, will be able to survey about 3 times as many. That gives us a sample size. 15 to 20 Earth-sized planets in habitable zones, searched for oxygen within the next 15 years. If even one of them shows a strong oxygen signal, combined with methane or nitrous oxide or dimethyl sulfide, the odds that we are alone in the universe drop to nearly zero. And if none of them show biosignatures, that is also useful data. It tells us that life is rarer than we hoped, that Earth is more unusual than we thought, that the conditions required for biology to start and persist are stricter than the optimistic models suggest. It narrows the search, it refines the parameters, it forces us to ask harder questions about what we are looking for and whether we are looking in the right places. The philosophical weight of this cannot be overstated. For the entirety of human history, we have been alone, the only intelligence we know about, the only species capable of asking questions about its place in the universe. That loneliness is about to end one way or another. Either we find evidence of life and we learn that we are not alone, that the universe has produced biology more than once, that there are other worlds out there where chemistry crossed the line into metabolism and replication and evolution, Or we search dozens of planets and find nothing, and we learn that life is so rare, so fragile, so dependent on specific conditions that Earth might be the only place in the observable universe where it happened. Both answers are terrifying in their own way. One tells us the universe is full of life, but so vast that we might never meet anyone. The other tells us we are alone on a scale that is almost incomprehensible, drifting through a cosmos of dead rocks and gas clouds with no one to talk to but ourselves. The solar system has been preparing us for this. Every hostile planet, every extreme environment, every world that would kill you in seconds has been a lesson in humility, a reminder that the universe is not built for us. That Earth is not the default, that most places are hostile, and the few that are not are rare and fragile and probably temporary. Venus did not start as a hellscape, it became one. Mars did not start as a frozen desert, it became one. The same could happen to Earth if the variables shift. The greenhouse effect could lock in, the magnetic field could weaken, the atmosphere could be stripped away. We are not immune. We are just lucky, and luck does not last forever. But the solar system has also taught us something else. It has taught us that hostile worlds are not boring. Venus is hostile, but it is also fascinating. The chemistry happening in its atmosphere is unlike anything on Earth. The surface pressure and temperature create conditions that do not exist anywhere else in the solar system. Titan is cold, but it is also active. The methane cycle, the organic chemistry, the lakes and rivers and rain, all of it makes Titan one of the most interesting places to study. Pluto is frozen, but it is also geologically young. The glaciers, the mountains, the atmosphere that freezes and thaws, all of it tells a story about a world that is still changing. Hostile does not mean dead. Extreme does not mean simple. The most dangerous worlds in the solar system are also some of the most complex, the most dynamic, the most worth studying. And that will be true for exoplanets as well. The hot Jupiters being torn apart by their stars are teaching us about atmospheric escape and tidal forces. The super-Earths with rock vapor atmospheres are teaching us about high-temperature chemistry. The rogue planets drifting in darkness are teaching us about planetary formation and ejection dynamics. Every extreme world, no matter how hostile, is a natural laboratory running experiments we could never replicate. And the more we learn, the better we understand the full range of planetary environments, the better equipped we are to recognize the rare exceptions, the planets where the conditions are not extreme, where the temperature is moderate, where liquid water is stable, where the atmosphere is thick enough to support weather but not so thick it crushes everything, where the chemistry is interesting but not deadly. The next 15 years are going to be the most important period in the history of planetary science. We are going to go from a catalogue of a few thousand exoplanets, most of them known only by their mass and radius, to a detailed database of thousands more, with atmospheric compositions, temperature maps, and in some cases direct images. We are going to find planets that make Venus look tame. We are going to find planets that make Jupiter look calm. We are going to find planets so strange, so extreme, so unlike anything in our solar system that they force us to rewrite the textbooks again. And somewhere in that catalogue, buried among the hot Jupiters and the lava worlds and the rogue planets drifting in darkness, we are going to find a handful of worlds that look almost normal, almost habitable, almost like home. And when we do, we are going to point every telescope we have at them. We are going to measure their atmospheres down to the parts per million. We are going to look for oxygen, for methane, for ozone, for any combination of gases that could indicate biology. We are going to watch them for years, tracking changes, looking for patterns, searching for anything that breaks the rules of chemistry and geology, and suggests something else is going on. We are going to do everything we can to answer the question that has been sitting in the back of every human mind since we first looked up at the stars and wondered if anyone was looking back. And the solar system, with all its hostile worlds and extreme environments and nightmares frozen in ice or cooked under crushing atmospheres, is the reason we will know how to ask that question properly. The reason we will recognize the answer when we find it. The reason we will understand what makes a planet habitable and what makes it hostile. The 8 planets and their moons are not just our neighbors, they are our teachers. And the lessons they have taught us about heat and cold and pressure and wind and radiation, about feedback loops and tipping points and the fragility of atmospheres, about the narrow boundaries that separate life from death on a planetary scale, are the tools we need to explore the galaxy. The universe is vast, it is ancient, it is full of planets, billions of them, maybe trillions, scattered across hundreds of billions of stars. Most of them are hostile, most of them will kill you, but some of them, a tiny fraction, might not. And finding those planets, recognizing them, understanding them, is the great project of the next century. The solar system is where we learned how. The terrifying worlds in our own backyard are the training ground, the laboratory, the textbook, and everything we learn from Venus and Jupiter and Titan and Pluto and every other hostile place we can reach with a spacecraft is preparation for the day we finally turn our telescopes outward and start searching in earnest for the rare exceptions. The pale blue dots orbiting distant stars, the worlds where the chemistry went right and the climate stayed stable and life maybe had a chance. That day is coming. The telescopes are being built, the missions are being planned, the technology is ready. And when it happens, when we finally find that first unambiguous biosignature in the atmosphere of a planet orbiting another star, we will look back at the solar system and remember all the things it taught us, all the extremes we mapped, all the dangers we catalogued, all the hostile worlds we studied so we would know, when the moment came, what we were looking at. The future of fear is not about being afraid of what is out there. It is about being prepared, about understanding the full range of what is possible, about recognizing the boundaries so we can find the places where the boundaries do not apply. The solar system is terrifying, but it is also beautiful, and it is ours. The only collection of worlds we can touch, the only planets we can visit, the only laboratory we have for studying how planets work in detail. And it has been teaching us, one hostile world at a time, how to read the universe. How to look at a distant planet and see past the numbers, past the mass and radius and temperature, and understand what kind of place it really is. That skill, hard-won over decades of exploration, is the key to everything that comes next, to finding life, to understanding our place in the cosmos, to knowing whether we are alone or just one voice in a chorus so vast we have barely begun to hear it. The extremes are not the enemy. They are the map, and we are finally learning how to read it. You have been looking at planets your entire life. Venus in the evening sky, Mars hanging red above the horizon, Jupiter bright enough to cast shadows. You looked up and saw lights, wandering stars, objects that moved but did not change, beautiful, distant, harmless. Now you know what they actually are. Venus is not a light, it is a warning. A planet that started with the same materials as Earth, assembled in roughly the same region of the solar system, and ended up as a 900-degree oven wrapped in sulfuric acid because a few feedback loops locked in and never stopped. Mars is not a distant beacon, it is a grave. A world that had oceans and a thick atmosphere and lost both because its magnetic field died and the solar wind stripped everything away over billions of years. Jupiter is not a serene giant. It is a radiation furnace surrounded by storms that have outlasted human civilization. Neptune is moving air at speeds that should not be possible with the energy available. Pluto is so cold that the atmosphere freezes out of the sky and falls as snow for decades at a time. These are not distant curiosities, they are demonstrations, case studies in how planets evolve and what happens when the variables shift. Earth is not the default configuration. Earth is the exception. The one planet out of 8 that landed in the narrow band of conditions where water stays liquid, where temperatures allow chemistry, where the atmosphere is thick enough to support weather, but not so thick it crushes everything, where a magnetic field shields the surface from radiation, where plate tectonics recycle carbon and stabilize the climate over billions of years. That configuration is not guaranteed. It is not permanent. It is not even common. The solar system tried 8 times to build a major planet and succeeded once. Venus shows what happens when the greenhouse effect runs away. Mars shows what happens when the atmosphere is lost. The ice giants show what happens when you move too far from the sun. Mercury shows what happens when you strip away the atmosphere entirely. Every planet is a test case. Every failure teaches us something about the rules, and the rules are harsh. Most places in the universe are not safe. Most places will kill you. Most planets are defined by extremes that human biology was never designed to handle. Heat, cold, pressure, wind, radiation. The 5 categories of planetary horror, and every hostile world falls into at least one. Venus is heat and pressure. Jupiter is radiation and pressure and wind. Titan is cold. Neptune is